Welcome to ACM WiSec 2021, the 14th ACM Conference on Security and Privacy on Wireless and Mobile Networks. My name is Christina Pöpper and I'm here with my colleague Mathy Vanhoef, and we will guide you through the online experience. Welcome and marhaba to this 4-day technical conference. So we will have 4 days of technical presentations plus 1 day for tutorials and in parallel the ACM 2021 workshop. This is going to be the second edition of a fully virtual conference following the experiences from last year. So depending on where you are right now in the world, it might already look more normal to you, or you are still living and working under severe restrictions. It turned out that going virtual was the right decision for us this year because up till now, unfortunately, we are not allowed to welcome any visitors on campus up till now. We will have the typical 3-day technical program of WiSec spread out over 4 days, in such a way keeping the advantages of a single-track conference, but doing this while having less screen time per day. We will enable live interactions via Zoom for the video talks you're attending via Zoom right now, and we will have an online virtual conference setup consisting of Slack and GatherTown. The time zones have to be optimized for participants from the eastern part of North America, from Europe, and the western part of Asia. We are well aware that it may not be perfect for everybody, but it will hopefully enable a good participation for the majority of our participants.
Thank you, Christina, and once again, welcome everyone to WiSec 2021. So if we look at the registration,
welcome to ACM WiSec 2021, the 14th ACM Conference on Security and Privacy on Wireless and Mobile Networks. My name is Christina Pöpper and I'm here with my colleague Mathy Vanhoef, and we will guide you through the online experience. Welcome and marhaba to this 4-day technical conference. So we will have 4 days of technical presentations plus 1 day for tutorials and in parallel the ACM 2021 workshop. This is going to be the second edition of a fully virtual conference following the experiences from last year. So depending on where you are right now in the world, it might already look more normal to you, or you are still living and working under severe restrictions. It turned out that going virtual was the right decision for us this year because up till now, unfortunately, we are not allowed to welcome any visitors on campus up till now. We will have the typical 3-day technical program of WiSec spread out over 4 days, in such a way keeping the advantages of a single-track conference, but doing this while having less screen time per day. We will enable live interactions via Zoom for the video talks you're attending via Zoom right now, and we will have an online virtual conference setup consisting of Slack and GatherTown. The time zones have to be optimized for participants from the eastern part of North America, from Europe, and the western part of Asia. We are well aware that it may not be perfect for everybody, but it will hopefully enable a good participation for the majority of our participants.
thank you, Christina, and once again, welcome everyone to WiSec 2021. So if we look at the registrations, we can see that we have attendees from all over the world. So we have the US and Canada, we have several countries from Europe and also Asia. If we then look at our participants, we can see that a large amount of them are PhD students or regular students, and also a significant amount are professors. And this is followed by researchers and people from the industry as well. So we have a good representation here.
What can you expect from the next couple of days? We will have 3 keynote speeches, the first one on privacy and IoT, a second one on artificial intelligence and IoT, and the third one on security in next-generation wireless networks. We will have 34 technical paper presentations. The papers are going to be made available on the ACM digital library that you will be able to access via our conference website. And we have 4 among those 34 papers that have been awarded with the replicability label. Particularly watch out for those. We will have a panel discussion on digital vaccination passports on Wednesday. We will have a dedicated poster and demo session where 6 demos and 5 posters will be presented. We're going to have 8 tutorials on wireless research frameworks on tools, as well as social gathering enabled on GatherTown, and there will always be an award ceremony taking place on Wednesday this week. How do we enable the conference? I mentioned there are 3 systems that will interact with each other. So we have Zoom, where the videos and recordings and live presentations by the technical papers will take place. It's also where the Q&A session will happen, and we will use it for announcements and celebrations. Then we have our Slack system that will hopefully support chat and interaction among the attendees, use it to discuss and ask questions for the technical sessions and get them answered either on Slack directly or on Zoom. You should all have received invitations to our Slack instance by now. We also enabled the Random Coffee app in order to facilitate interacting with people you might not have met before. So do use that in order to get in touch with somebody on Slack who you may not have talked to before, and use it as well. Use the Slack system to get back in touch with people who you just haven't seen in a while. GatherTown is there for socializing, for video chatting with fellow attendees. We will also have the demo and poster session taking place entirely on GatherTown, and it will be an opportunity for our attendees, for you to talk to keynote speakers and panelists.
So to give a bit more background on GatherTown, you can see here the map that we will be using during the conference. So on the left hand, you can see, for example, the beach. This is where you can walk around and try to meet and talk with other attendees. So the way that GatherTown works, if you walk close to someone, your webcam and microphone will automatically activate and you can talk to them. Next to the beach, you can see the conference hall, and this is the place where you can stand when an actual presentation is going on. Then in the middle, under the palm trees, this is where you will start when you first join the GatherTown instance. And right under the palm trees on the right and left-hand side, there are also 2 small information desks that contain more information about how to use GatherTown. And this information is also available on the Slack channel. Above the palm trees, you can see blue and red squares. If you enter these squares, you can talk to fellow attendees that are also inside these squares. So this allows you to hold a semi-private conversation with other people as well. And finally, on the right-hand side, this will be the place for the demo and poster sessions. So every demo and every poster will have a whiteboard there, and you can interact with this whiteboard to, for example, see the paper or see other material about the demo and poster. And you will also be able to interact with the authors in this area. So during the conference, we ask you to follow several guidelines. First and for all, try to interact as much as possible with fellow attendees and try to do this in a respectful manner and always assume the good intent of the other person. As mentioned, we also have a live streaming of the event on YouTube, and this streaming on YouTube is public, so feel free to share this link on Twitter, on Facebook, or with your fellow colleagues and students at your university or company. If you think there is anything missing, don't hesitate to tell us and we will try to address this. During the conference, we will have a zero tolerance for abusive behavior. So if you notice anything going on, please inform us. Please also don't share any abusive material. And here also try to be mindful that something can be abusive in one culture, but not in the other. We also realize that mistakes can happen. If that happens, we hope that you will approach this in a constructive manner and give constructive feedback. Finally, please don't share the Zoom and Slack link. These are private links only for attendees, as well as the GatherTown. This is also private for attendees.
Thanks, Mathy. Right after this opening session, we will start with our first technical slot on IoT security. We will have 3 keynote presentations. The first one starting today with Stacey Higginbotham talking about privacy in an era of IoT. We'll have the second keynote presentation given by Wenjuan Xu tomorrow on artificial intelligence meets IoT. And the third keynote given by Malik Tatipamula on Thursday on securing the next generation wireless networks. Later today, at the end of today, we will have our social gathering on Gather Town, so please plan to attend this as well. On Wednesday, we would like to point to the panel discussion on digital vaccination passports that's going to be moderated by René Mayrhofer. And we will have the tutorials starting on Thursday with the first tutorials on SDR and GNU radio that will be followed by 7 tutorials on Friday. In parallel to the tutorials on Friday, the ACM WiSec ML workshop will take place. If you are a registrant, which you are here for ACM WiSec, then you are also allowed and invited and encouraged to participate in ACM WiSec ML. Just make sure that you click on the separate Zoom registration link to be able to access the Zoom space of the workshop as well. Setting up. Sorry, I give back to Mathy.
Thank you. So this year, WiSec will again be present on both Twitter and YouTube. So if you also happen to be a Twitter user, feel free to tweet about the conference so we can share the presence about the conference. As mentioned, WiSec will also be live streamed on YouTube. But apart from that, we also already published some teasers about both the tutorials and presentations during WiSec. So we could recommend that you also check out those teasers on YouTube.
We continue with the traditions of WiSec and have again had this year a fast review cycle that the TPC chairs will comment on in a moment. We also do have again the replicability label that has been assigned to the 4 listed papers that you can see on the slides here. This is an important part of WiSec. It's an important part of our research process, so we continue with the replicability label assignments. New this year, though, is the first time we have a SOC paper, systematization of knowledge paper, that followed the call for papers on the SOC category. As mentioned, we will have tutorials for the first time this year on wireless frameworks and tools to enable wireless security research. And we also emphasize this year's strong use of shepherding and revision options for the review process. Setting up this whole program of ACM WiSec would not have been possible without a big organization team. Our thanks first and foremost go to the chairs of the technical program committee, Lejla and René. Also the poster and demo chairs, Merve and Erik, have done a great job in bringing that the poster and demo session into the virtual space. So please make sure to attend the poster and demo session on GatherTown. Our publicity chairs, Adrian and Gabriele, did a wonderful job in announcing the events that happened during this week and on tweeting about them. We've had the reproducibility chairs, Anjan and Brad, who took care of assigning the replicability labels. Our publication chair, Shujat, did a wonderful job with the proceedings. The tutorials were organized by Yiska, who managed that on her own, bringing the tutorials to life. And we had a web team consisting of Raluca and Liang, who supported putting up the website, and our registration team with Nora and Hari, who helped on the registration processes. Behind that, for the virtual conference, there are a number of more people involved with setting up the virtual space for you for this conference. There are people that will support the Zoom meeting management. We have a big team from our university on the audio and video team and live streaming that help to support this online experience for you. There's also from the Center of Academic Technology that supports us, and we have the finance team from NYUAD with Hector and Claudia, who supported the registration process. With that, we would like to hand over to Lejla and René to report on the technical program committee work.
Christina, thank you, Mathy. So this is very warm welcome from your program chairs. My name is Lejla Batina, and together with René Mayrhofer, I had the pleasure to be program chair for WiSec. So with this, I would like to just summarize a little bit of what we've been through in this, starting from December when we got together to organize this. It's been like several months, and what I can say is that for us, this change of like not having normal physical conferences but going online didn't impact us as much as obviously as the conference itself. So say like our procedure was just business as usual. And with the numbers, as you will notice, we kind of got where WiSec was usually with like quite some number of submitted papers and so on. So let's just remind everybody on what it was actually. So as you know, WiSec only has one submission deadline, and that most likely is the way it is. But for some people, it just works very well. We all know it's coming sometime in March, and then it's that's where WiSec deadline is, and then the conference in June or so. We have received 128 submissions after desk rejecting 6, which were out of scope or some blinding issues. So it was kind of very, very healthy number of submitted papers, some short papers, for the first time, some SOC papers, as you heard from Christina. We have lined up 54 program committee members. We want to thank them all. That's coming on the next slide. And we had like the usual deadlines, trying to give people a break for weekends. So yeah, kind of ending it all on Friday or even before to make sure that like people can at least enjoy weekends. What happened is, like as usual, very quick turnaround. We basically used only 6 weeks from submission to auto notification. So that put a lot of work on our committee members. And yeah, they of course use some external reviewers when needed, and they all worked really hard to provide high quality reviews. We noticed a lot of papers needing some shepherding this year. So we had in total 18 conditionally accepted papers where we assigned the shepherd, and there we were all, of course, always super happy with the responses from our committee members as well. So after the reviews, they also always reacted very warmly to additional tasks to do also shepherding. So only 16 were without accepted. So actually majority of papers require some kind of additional touch. So next slide. Speaking of our TPC, so our program committee is listed on this slide. I'm not gonna read them all, so you can see we have collected people from around the globe, from all the continents. Some are well known to WiSec attendees. Some are also more junior and serving for the first time. And we thank them all for the great job they did for this event that we hope to be a great success. And with this, I hand over to my co-chair, René.
Thank you. Next slide, please. I'm sorry that I can't seem to be able to start my video right now in Zoom. I'll just do the voiceover for the time being. So, now there it is. As might be a major surprise for many of you who've been in program committees, but is always a stressful situation to the program chairs, that reviews do come in the last 3 days. And I would like to extend our apologies for many of the nagging emails and continue to thank all of you members of the program committee. Without all of you, we could not have made this program. We could not have put it together in this form. What you will also see in this graph is that we actually had a second half round of reviews there, where we asked for additional reviews, and you can see those coming in, of course, after the official review deadline still. And this is what I think makes WiSec still pretty unique in this area. We managed to keep to that very tight turnaround time of only 6 weeks. Next slide, please. In the end, we managed to accept nearly 30% of the papers. That is one of the nice side effects of this conference having been planned from the start as a virtual one. and the virtual one spread over 4 days, meaning that we could easily extend the number of sessions and the number of slots within the sessions just by a little to increase our acceptance rate and allow more members of the community to participate actively as authors, as presenters in this conference. However, what has already been mentioned, we focused very heavily on a shepherding process. So as part of our extended second half of the review cycles, we also assigned shepherds to the majority of our, at that point, conditionally accepted papers. 18 papers were conditionally accepted, as you can see, which is more than those papers that were directly accepted. And happy to say that all those papers did in the end get accepted into the final program. And we strongly believe that this shepherding phase as an in-between one deadline and multiple rolling deadlines did help improve the papers that we now have in our program. Next slide, please. As this is a virtual conference, we have not actually run the statistics on submissions from different countries because we knew it would be virtual. And so instead of talking about submissions and accepted and rejected papers by countries, we chose to rather list it by, for example, the topics. We had a wide range of topics for this year's WiSec call for papers, but as you can see, there are a few topics that did seem to be very popular, including cyber physical systems and IoT. But also, of course, as the main WiSec focus stays here for local wireless communication and the additional implications on physical tracking and location, probably also inspired by the discussions that we had over most of the last year on contact tracing and the privacy implications. Cryptography, general privacy, anonymization, usable security and privacy have always been strong parts of WiSec programs as well, and we see the same this year. You might also see in those graphs that mobile applications, papers on mobile applications seem to have been more difficult to write at this point. Maybe because so much has already been studied, maybe also because the platforms continue to mature and doing another analysis on additional potential vulnerabilities of such platforms does become increasingly hard. But if you compare those figures here, then there's also quite a lot of papers in the IoT, in the cyber physical and IoT space that did not make it into the accepted program. I, of course, do not want to take these numbers as an indication of which papers you should be working on for next year, because as always, metrics that are used for driving decisions become poor metrics, and I propose hereby to not use this metric again in the next years. Next slide, please. The same, we could run, for example, the analysis of how many authors did successful papers have. And very unsurprisingly, if you have a small, tight group of co-authors here, as we saw between 2 and 5 co-authors on a paper, then the chances of acceptance seem to have gone up this year. While with only 1 author, we didn't have a single paper accepted, neither did we have with more than 6 authors. Again, no indication of how many authors you should invite for collaboration next year, but I found those interesting. And with that, I would like to hand back over to Christina and Mathy, and I would just like to ask for a little bit of patience with us finalizing the final numbers on a more detailed written report on a technical program that we're going to release by the end of the conference, because we also want to have something about our awards ceremony, like the Distinguished Paper Awards, in that document. Back to you.
Thank you to our technical program committee chairs. We are now ready to start the conference. We will have 3 technical sessions today, as well as a keynote presentation by Stacey Higginbotham on privacy and IoT. I would like to remind you to keep in mind the socializing event at the end of today, at the end of the conference day on Gather Town. And with that, we are ready to start the first technical session. We will hand over to the first session chair, Gerhard Hancke, and we hope that you do enjoy the conference.
Thank you. Thank you very much. Welcome all. So I'm Gerhard Hancke. I am with the Department of Computer Science at the City University of Hong Kong, and it's a pleasure to act as the chair for the first session of WiSec 2021, which is on the topic of IoT security. So this is an area with interesting security problems, given the scale of IoT deployment, both in terms of devices and the amount of data we're dealing with. The number of different technologies or systems we are working with, and especially its interaction with users and its environment. So we have 3 full papers to be presented, and these will actually touch on all these issues. The session is allocated about 60 minutes. We'll see how it goes. So we should finish about 7:20 GST. So a brief reminder of the format. First, the 3 papers will be presented. As I understand, these are all recorded videos, right? And then afterwards, we'll circle back and we'll do the Q&A. So while the talks are ongoing, you can let us know your questions on Slack. If you really cannot get Slack to work, I'll also watch on the Zoom chat. Please just indicate what paper you are actually asking your question about. And I'm happy to then present those questions to the authors at the end. Right, so let's move on to our first paper, misactivation detection and user identification in smart home speakers using traffic flow features. So the paper focuses on 2 security issues that arise with the use of smart speakers and present network flow fingerprinting methods to mitigate the impact. The reviewers found that this was quite an interesting paper because misactivation detection and user identification in smart home speakers is considered an important issue with voice assistants, which increasingly find our way into our households and therefore is of great practical interest. So let's now hand over to the floor to the authors to hear their presentation. Thank you.
Hello everyone, I am Batyr, Charyyev, PhD candidate in system engineering from Stevens Institute of Technology, and today I would like to talk about our work on misactivation detection and user identification in smart home speakers using traffic flow features. So let me start our presentation. Smart speakers, also referred as voice assistants, are widely utilized in our daily life. Around 21% of the US households with internet access use smart speakers, and its market value is expected to reach 35.5 billion by 2025. Simple utilization of the smart speaker is as follows. End user initiates a voice command to the smart speaker and it executes it and replies back to the end user. However, smart speakers can be misactivated with accidental triggers, and as a result of such misactivation, user privacy can be compromised. For example, studies show that accidental triggers such as cocaine, similar to the wake word of the Microsoft Cortana smart speaker, can misactivate the smart speaker. And since manufacturers employ contractors that manually transcribe and annotate the audio recordings to improve the human speech recognition systems, such contractors may find themselves listening to the private conversation of the end users. Unfortunately, previous studies show that misactivation of the smart speakers happens quite often. For example, researchers from the Northeastern University show that smart speakers misactivate 1.43 misactivations in every 10,000 words. And another study showed that reported around 1,000 accidental triggers that can misactivate the device. And around 75% of them have medium to high reproducibility. Of course, manufacturers put effort to reduce such misactivations, such as using lightweight DNA models or using acoustic fingerprinting techniques with a database of current airing advertisements to reduce misactivation of the smart speakers. However, previous studies show that despite to these efforts, smart speakers misactivates quite often. So in this study, we focus on the misactivation of the smart speaker, and we try to detect it with the network traffic features of the device. So specifically, we focus on the threat model shown in the figure. There exists a smart speaker, and it can misactivate with the voices coming from the TV or radio, which contains accidental triggers. And as a result of such misactivation, private conversation of the users is recorded and sent to the cloud. So victim is any person in the microphone range of the smart speaker, and the adversary is any party that can access recorded data received from the speakers, such they may include manufacturers or malicious actors which had unauthorized access to the data. And threat is any private and sensitive information that can be inferred from the recorded audio data. So the reason why we think the network traffic features can be utilized for this purpose is previous studies on voice command fingerprinting showed that the different voice commands on the smart speakers generate different traffic patterns. For example, this graph shows the simple traffic rate of two different voice commands. For example, we can see that voice command from Alexa, what is Roblox, and what is my sport update. They have two different traffic rates. The traffic rates of these two voice commands can be distinguished, separated from each other. So we think that traffic patterns of the accidental trigger and traffic patterns of the wake word can be separated from each other, and this will enable us to detect the accidental triggers. So another thing that we explored in our study is the user differentiation. This will enable us to detect malicious users which try to impersonate the device owner and to perform malicious activities such as bank transactions or changing log configurations, etc. So victim is the owner of the smart speaker, and the adversary is any party that can direct the wake word or malicious user voice commands to the smart speaker, and the threat is any malicious activity that can be performed to the smart speakers. So to detect the misactivation of the device, we employ two approaches. First one is using the locality sensitive hashing, and second one is using machine learning models such as one-class classifiers and autoencoders. So in the first approach, specifically we use the nil-Simpson hashing, a locality sensitive hash method. Nil-Simpson generates the similar hash values for the similar inputs. So basically, first we store the signatures of the wake words in our database. These signatures are created by giving the raw package data of the wake words to the nil-Simpson hash function, and it will generate us a hash of those wake words, and we will store it in a database as a signatures. So when new voice command is initiated, again, we generate a hash of that voice command and compare to the existing signatures. And if it deviates a lot, it means that voice command is an accidental trigger. Similarly, for machine learning models, we train them on a wake word data of the smart speaker, and the accidental triggers are detected as outliers. In our evaluation, we also evaluated ensemble learning by ensembling multiple models and taking the majority voting of the model to give the final prediction result. So data sets used in our studies are, for misactivation analysis, we used 4 smart speakers, and the data was collected by researchers from the Northeastern University. The smart speakers include Amazon Echo Dot and the Google Home Mini, etc. Authors basically analyzed in their study how frequently the smart speakers are misactivated by playing 12 different TV shows near the smart speaker and recording the time when they misactivated. Second dataset used for user differentiation is collected from 2 smart speakers, Amazon Echo and Google Home. This was collected by researchers from the Cincinnati University, and in their study they use this data to analyze the voice command fingerprinting. Basically, they issue 100 different voice commands on smart speakers and repeat them 300 times with 5 different voices. So for future selection, nil-Simpson uses simple hashes. For one-class classifiers and autoencoders, we collect the numerical features from the existing protocols in the traffic data, and we rank those features and take the top 3 features. Of course, we tried the top 4 or top 5 features. However, we observed that the best result is obtained the top 3 features. So in our analysis, we showed the results for the top 3 features. Of course, before ranking the features, we made the correlation analysis and variance analysis. Then we ranked the features based on the univariate feature selection, recursive feature elimination, and forward sequential feature selection. The top 3 features for each smart speaker is provided on this table. And for implementation of one-class classifiers, we used isolation forest. We used scikit-learn, and the one-class classifiers include isolation forest and local outlier factor. And for implementation of the TensorFlow, we used our encoders. So let me present you the results. We split the data as 70% for training and 30% for testing, and the major metric used in our analysis is array under the curve. So this figure shows the misactivation detection results. For each smart speaker, we can see that for each smart speaker, there exists at least one model that achieves array under the curve score of 99%, except for the invoke. These results show that the models can detect the misactivation of the device using simple traffic flow features and achieve a good results. So in terms of the user differentiation, the best ensemble model is a Niel-Simse local outlier factor and autoencoder and their combination. And we observed that best ensemble model achieves array under curve score above 70% for Amazon Echo and above 80% for Google Home. And we also tried to analyze if there exists some voice commands for which models achieve really good results, and if there exists some voice commands for which they perform poorly. So this figure showed the results for the Niel-Simse for each individual voice commands, and we observed that Niel-Simse achieved array under curve of 80%, above 80% for all users, with 20 voice commands and over 70% for 40 voice commands. Similar results were achieved for other models. So basically this showed that there is some voice commands for which models can successfully be used to differentiate the users. So we also analyzed the processing cost. To do that, we used the Raspberry Pi and we used the tools such as PCUtil. So this model can be used, the models to detect the misactivation of the device can be used in the local router or can be deployed to the simple Raspberry Pi that can be used as a local gateway. So we analyzed the processing cost after the deployment, because training can be done on the local powerful machines, and the thing that we focus on is the after processing cost after deployment. So we observed that overall response time is less than 1 second, except for autoencoder, and the CPU requirement and memory requirement is reasonably low. So we also want to emphasize that we didn't perform any optimizations. However, we believe that processing cost can be further reduced with parallelism or using the lightweight libraries such as PK++, written in C++, and using the TensorFlow Lite designed for the edge platforms. So the limitation of our study and the future work can be we didn't analyze the network traffic characteristics that might change due to the hardware variations, or we didn't analyze the impact of the age, gender, spoken language difference. Also, one might argue that there exists limited number of users and voice commands in our datasets, which is 5 users and 100 voice commands. So, however, we believe that based on 2018 statistics, the average American household size is 2.53. So we believe that since in our study we focus on 5 users, we believe that our study gives some insight applicable to the most of the households in US. So this is the end of my presentation. If you have any questions, I will be happy to answer your questions. Otherwise, thank you so much for listening. Thank you.
Thank you very much. Okay. So just a reminder to have those questions on Slack or in Zoom if you have anything to do. Right. Okay. So moving on to the second paper. So it's non-IID data by rebalancing at IoT edge with peer-to-peer federated learning for anomaly detection. So this paper proposes a peer-to-peer algorithm to train supervised anomaly detection machine learning models. It's targeted at environments where we don't have independent and identical distributed data. It also includes a mechanism to locally rebalance these training sets. The problem of federated learning with non-IID and unbalanced data is a practical and important problem in IoT, especially the tendency for edge nodes to locally store and process data and to train also anomaly models, right? So the reviewers felt that this was especially topical given the deployment of machine learning in IoT in general and the need for anomaly models to be created. So let's now hand over the floor to the authors.
Hello everyone, I'm Wang from Cybersecurity Unit at RISE Research Institute of Sweden. I am going to present our work on the novel approach to data rebalancing with peer-to-peer federated learning for anomaly detection. First, I will introduce our motivation and goal. Federated learning is a very promising paradigm for training distributed machine learning models. It has advantages includes privacy preserving, efficient resource utilization, and so on. As shown in the top right figure, federated learning allows to train the machine learning model collaboratively so that each client in the learning task train the model locally using their own dataset for a reduced number of epochs. And then they send the resulting model to the central node, which merging the local models and by the participant into the global model that is sent back to the clients. However, general federated learning may not be practical in the real-world setup because it depends on the different IoT network deployment and configuration. The network connectivity can be limited. Not all the clients can access to the central node in this case. On the other hand, the IoT network data usually are known, independent and identically distributed, and imbalanced. And shown in the bottom right figure, 3 different clients have their own local data distribution. The local model can not have a whole picture to the global data distribution. It may degrade model's performance. Therefore, in this paper, we propose peer-to-peer federated learning, which there are no central node to coordinate the learning task. The model weight and information only be shared with connected clients. We propose a novel approach to addressing imbalance and non-ID dataset for anomaly detection. The approach is that adaptively applied in peer-to-peer federated learning, and in this framework, the model can be independent and personalized. The adversary to our work are the compromised devices. We aim to detect them as soon as possible and isolate them from the IoT network. In our framework, there is no central node nor a global model to maintain. Since the adversary's attack is not our focus, so we assume that device is benign when the first joining the network. Our method has shown its effectiveness in 4 scenarios. First is when the data are unbalanced and IID. Second, the method can be applied when the data are IID but imbalanced. Third, even when the proportion of benign and malicious sample is not the same. For example, there can be some clients with more malicious traffic than benign. Last, like many real-world settings, we consider the case where distribution of benign and malicious traffic varies across devices and thus across clients. Thus, each client has its particular data distribution. In the next few slides, I am going to introduce our approach. First, I would like to introduce some classical rebalancing techniques, and one of them is a state-of-the-art. Downsampling is randomly removing the samples from the majority class. Oversampling is randomly deduplicating the samples from the minority class. SMART is a well-known state-of-the-art method that generates synthetic points. For every sample from the minority class, SMART finds its nearest neighbor and applying linear relation between the selected sample and one randomly chosen neighbors in order to generate the synthetic points. K-SMART is our proposed method. It improves SMART by instead of consider only one chosen neighbor, but rather all the neighbors to generate synthetic samples. And K-SMART only randomly select K sample from minority class to generate per one time. Compared to SMART, the synthetic sample can be generated in the region instead of a one-on-one line. In the detail, we can divide K-SMART into a few steps. First, we need to decide how many number of synthetic points to be generated. Second, we randomly pick K samples in minority class and decide the number of synthetic points to be generated by one sample. Third, we pick n nearest neighbor of one selected sample. Finally, the synthetic points will be generated by following iteration. From the bigger scope, we design a framework of peer-to-peer federated learning where we apply K-SMART too, and we call it P2P K-SMART. As shown in this figure, at every client, we first use K-SMART to generate synthetic points in order to rebalance the local dataset. At the same time, the generated synthetic points by the one client are going to be shared with the other connected client. Take the figure as an example. C1 is connected with C3, so the synthetic points generated by C3 are going to be shared with C1. We also apply federated averaging to update the local model weight and the connected nodes. As you can see in the dot arrow in the figure, the p-value is the weight to the client. It considers the variance and data size of the local dataset. For instance, the local model weight C1 is going to be updated by the influence from C3. In detail, the whole process can be divided into few steps. First, the local model at every client is initialized. Then, case mod is used to imbalance the training dataset. If there are any external synthetic points provided by other clients, they will be joined to the training set. Then, the model is trained locally. When in the merging and updating phase, we first pick random number of clients to update. Then we apply federated averaging and receive synthetic points from the connected clients. To be simple, the workflow of the training procedure can be depicted as its figure. The cloud only participates in the beginning to deploy the initial model to every participant client. After that, cloud is removed from the learning task. At every client, the training procedure is done parallelly. After local training, the chosen clients update the local model weight and join the external synthetic points to the training set from the next round training. Due to the presentation time limit, for next few slides, I will show some most important experiments. Some other minor experiments can be checked in this paper. For the following experiment, we use two real-world datasets. First one is E-IoT. This dataset is collecting real-world traffic data, gathering from 9 commercial IoT devices asymptotically infected by midlight and batch light. The data has been proceeded to statistical traffic flow data. Second dataset is also the collection of 5 simulated IoT devices are under botnet attack, including DDoS, DOS, service scan, and so on. They have picked top 10 features. We will use them into our experiment. First, here is the experiment result of P2P case mod on the case of global imbalanced Non-IID data. We compare our approach to the other 4 baselines. The general metrics for evaluation such as AUC and F1 score are not fair in this case of imbalanced data. Therefore, we use false negative rate, false positive rate, precision and recall 75% and recall at precision 75% as our metrics. As you can see in the figures, the red line shows our approach can achieve almost 0% false negative rate in both datasets and reach 100% precision and recall. The other method, on the other hand, has an overfitting problem. The precision and recall drop a little bit in the end of the training. This set of experiments have proven that our method has the best performance in the scenario. Second, if we evaluate our method in the case of whole, is when there is one client has opposite situation to the other clients. Particularly speaking, that some clients in IoT network are under floating attack, which means anomaly traffic is the majority. Some other clients may have some passive attack that are harder to detect. In this setup, both client A and B has more benign traffic than anomaly traffic, but client C has more benign traffic than anomaly traffic. The result shows in the figure on the right-hand side, our method reached 0% of false positive rate, while false negative rate keeps 0%. And our method performs best in the precision recall. Therefore, our method is proved to be the best method also in this case. Finally, we evaluate our method in the case that is most challenging and the closest to a real-world setup. In this experiment, we choose 3 totally different IoT devices from NB-IoT dataset to make 3 clients has a non-IID data distribution. For UNSW BOT IoT dataset, we choose different types of attack for 3 clients. Client A is undertaking a scan attack, client B is undertaking DOS attack, and client C is undertaking DDoS attack. Here is the result to this set of experiments. Because this problem is more complex and different, it takes longer time to converge. As the result shows in the figures, in the non-IID setup, our method in the red line shows more obviously and even better performance than the other baselines in all metrics. For example, SMART in the green line has similar trend of learning performance as ours, but couldn't reach as high precision and recall as P2PK SMART. This phenomenon appears also in false negative rate and false positive rate. To sum up, our method has the absolutely outstanding performance in this challenging scenario. Finally, I would like to bring out some discussion. Hello everyone, I'm Wang from Cybersecurity directly applied in peer-to-peer federal learning. And sharing artificial synthetic points helps to solve the non-IID problem, and the points are difficult to be identified. Because there is no central node, we have less entities to trust, and limited information to be shared, with only specifically connected clients. And the shared information about anomalies enables the creation of the broader variety of synthetic points that enrich the local training dataset. Finally, since addressing a adversarial attack is out of our scope, but it is open to combine the techniques of robust aggregation, and we are leaving this problem for the future work. Thank you very much.
Thank you. Let's move on to the third paper. The third paper is LightningStrike, Insecure Practices of E-IoT Systems in the Wild. In this paper, the authors evaluate the security of enterprise Internet of Things. This work is impactful due to its practical nature and uses a testbed with Crestron devices that rely on CrestNet to design and demonstrate some practical attacks. And this raises some security awareness around a system not widely studied before. Let's now hand over the floor to the authors to hear their talk. Thank you.
Hello, everybody. My name is Puche from the Cyber-Physical System Security Lab at Florida International University. For today, I'll be presenting LightningStrike, Insecure Practices of E-IoT Systems in the Wild. Now, to give an outline of this work, in the introduction, we'll cover E-IoT systems, E-IoT protocols, communication buses. Then we'll jump into LightningStrike, cover the problem scope, the threats, and the architecture. We'll jump into attack implementation and evaluation, the discussion, and we'll finalize with the concluding remarks. So what are E-IoT systems, which are the core of this work? E-IoT systems are professionally managed smart systems. What does that mean? It means that these systems are maintained and installed by trained and licensed installers to maintain and install these systems. So these systems are common in places such as smart buildings, government and private offices, schools, yachts, and other locations. And they're useful in several use cases such as lightning control, access control, security, motorization, things like that. There's some examples of offices, equipment room, conference room, entertainment can be seen on the right there. So to support many different devices, E-IoT must support many different protocols with many of different vendors making these protocols. So a thing about these protocols is that some of these protocols may be entirely proprietary in nature. An example is CrestNet, which is a very popular E-IoT proprietary protocol used for Crestron devices. Now this CrestNet was actually developed by the E-IoT vendor, so it's a proprietary protocol developed by the E-IoT vendor. Wired communication buses are used and are common for proprietary protocols such as CrestNet. And however, this is a problem. The security of many of these protocols, since they're closed source, remains under research. Why? Because no information is available online. These companies are very closed with their products and their software, and they don't leave any definitions or anything that you can look online and see how these protocols actually work. So jumping into communication buses are common in E-IoT systems because they're convenient and they're reliable. They provide power and communication to connected devices such as interfaces and touchscreens. They're not susceptible to wireless interference, which is maybe a big thing in some locations. And they do require physical cabling. Now, one thing about communication buses is that restricted and common areas may share the same communication bus. So if a communication bus is wired from a conference room to the restroom, and then to a storage room, which is maybe a secure location, then all the devices there are sharing the same information, even though they're in different, maybe some devices in restricted rooms. Since AIoT devices can communicate over the same communication bus, an attacker, Mallory, can inject a malicious device into the bus, for example, a conference room or a restroom or any available location. They can go and eavesdrop on the communication, and they can also inject and replay messages in the communication bus shared by all these devices. Mallory can attack the AIoT system because proprietary AIoT communication relies on security through obscurity. Specialized security solutions are not commonly implemented, and in fact, they may not actually exist for proprietary vendor protocols. And the purpose of LightningStrike is to investigate if it is possible for an attacker to compromise the EIoT system through the communication bus and through this proprietary communication. For LightningStrike, we wanted to implement 4 different threats. The first threat is denial of service. Mallory disrupts the availability of an EIoT system with an action such as message spamming, just sending garbage into the bus until things stop working. Malicious eavesdropping, using the unauthorized access to eavesdrop on communication, know when doors are opening, know what's happening, know where buttons are being pressed. Impersonation, impersonating devices that are already connected to the communication bus. Replay, well, grabbing a message, replaying it, and causing undesired behavior, or often unauthorized behavior on the EIoT system. So here's the LightningStrike architecture. LightningStrike, per our definition, is a collection of proof-of-concept attacks that leverages weak proprietary communication protocols to an attacker's benefit. It is the interaction of 3 modules: the attacker client, the attack device, and the target environment. Now, the attacker client is what the attacker will use, usually a computer with the software, to communicate with the attack device, to perform the attacks. The attack device is the device itself inserted into the communication bus, which may be different from system to system. And the target environment is the EIoT system itself, the target environment, what the attacker, what Mallory is attacking. So to test LightningStrike, we created a testbed using common Crestron and CrestNet devices. Now, we picked Crestron because it is one of the most popular EIoT system vendors out there. In fact, if I was presenting this live, chances are that the AV system in the location where I'm presenting would be controlled by a Crestron system. It's very common in schools and presentation rooms, which is why we picked it. And it is used in 90% of Fortune 500 companies. It's a very, very popular system. Now, to implement the attacks, we implemented various software modules, and all these software modules were created open source tools using open source tools and libraries. So first, the monitoring module, we passively eavesdropped the active network bus communication without transmitting messages. That's what the module does. Injection module, just inject arbitrary messages into the communication bus. The flooding module, to just send garbage out and cause a denial of service condition by flooding the communication in the bus. The readdressing module changes and readdresses the configuration of devices in the communication bus. For example, one of the IDs of the keypads, or devices, which often will have IDs, and the filtering module, which will be used by Mallory to see information requested and to better process and parse and make it more human readable for her. So the first attack we developed was to demonstrate that a denial of service threat is possible in LightningStrike. We wanted to prove that we could do it. So the attack was implemented because of the denial of service condition through just packet flooding, and we found out we were successful. In a few seconds of just spamming and sending garbage into the communication bus, we're able to completely break, and we were able to completely stop any devices from communicating and from functioning. Now, this is alarming because if you have keypads that manage maybe panic buttons or open emergency doors or opening a door or shutting off electricity because there's a fire, you will not be able to operate any of these keypads. Why? Because the communication bus is being spammed and nothing is going to work. The interfaces that the users depend on to function these devices are not going to work. For the second attack, we wanted to see if we could do malicious eavesdropping, so we implemented the monitoring module. We activated, we began passive listening, and the attack was successful. All the packets were captured, could be read, could be interpreted. We could see in some of the packets the IDs of the devices. We could also see when activity was happening. When somebody pressed a button, you saw a spike in activity. When somebody turned on a light, there was another spike in activity. It depended. So whatever happened in the bus, we could see all the activity happening. And for the third attack, we wanted to prove both impersonation and denial of service at the same time. So we used the readdressing module to alter the CrestNet ID of a keypad. That's the ID used to identify devices within a CrestNet communication. We caused a conflict between two devices. Now the attack was successful because it caused a denial of service condition between the altered keypad and the existing keypad. That means they both stopped working. So both of them were unusable. Similar to the first attack, if devices are unusable and users rely on these devices to function the system, to operate maybe sensitive access control or the examples listed before in the background, then it's not a good thing that things become unavailable. Attack 4, we demonstrated a replay attack. We wanted to see if we could perform a replay attack to see if we could actually do something a little more alarming. We used the monitoring module and the injection module to capture and replay a light toggle command. So the attack was successful. We captured a key press, we replayed that message, and a light turned on as we requested with the replay attack. Now this is interesting because if something like a magnetic door or sensitive equipment or motorization, you can do a replay attack on it. It can activate a device, or you can open a door, give somebody access to a location that they shouldn't have physical access to, and who knows what could happen depending on where the E-IoT system is functioning. So in this work, through our attacks, we demonstrated that an attacker can easily compromise an E-IoT system through the communication bus. It's challenging to defend these systems against these threats because of several challenges. First of all, standardization. E-IoT systems will often all run their own different protocols, so it's going to be different from system to system. Legacy systems, systems are all just discontinued. The company went under and they do not exist anymore. Can't do anything about them, or more of there's no support for those devices. And proprietary protocols. If there's no information available, you don't know how the protocol works, you don't know security through obscurity, it makes it harder to research and to see and to find flaws in the protocol. It is difficult to defend because if you don't know how the protocol works, how can you suggest a defense mechanism? Now, as such, new E-IoT protocols must be designed considering LightningStrike attacks in mind. The systems must consider this, the developers must consider this, and think that attackers can take advantage of the network bus to compromise the system. In conclusion, E-IoT systems are often overlooked, but they control important components. LightningStrike demonstrates that a proprietary E-IoT communication can be compromised. Attacks can be developed easily to compromise E-IoT systems using open source tools, cheap hardware, low level of knowledge. For future work, we hope to develop a security mechanism to protect E-IoT systems against LightningStrike style attacks. We want to extend our attacks into other E-IoT proprietary technologies and protocols, and hopefully develop something bigger and better. We would like to thank our sponsors, as noted right here. And here's my information. I'm happy to talk to anybody. Send me an email. I'll respond, and thank you for sitting through the presentation.
Okay, thank you. So that concludes the presentation part of the session. So we have had presentations from all the authors for the 3 papers. Thank you very much. We will now move on to the Q&A part of the session. So we'll start with the first paper. So is there an author from the first paper present? Can we have you on camera, ideally? And can you unmute yourself for any questions?
I'm here. Yeah.
Hi. So if anyone has any questions, let me know. At the moment, I have a question. So reading your paper at the end, you had some interesting comment. You said that when you discussed limitations, you talked about hardware limitations, and it seemed like there was some variability in network traffic between the same devices, but when deployed in different countries or coming from different manufacturers or something like that. So you said you didn't analyze it as sort of future work, but that sounds interesting. Well, it almost sounds a little bit weird. Do you have any ideas why that happens? Why would the traffic from a device look different in, let's say, one country versus another?
So yeah, actually it's analyzed by researchers from Northeastern University, the group of David Chalkness. So I think most of you maybe already know IMC paper they published in IMC. So in their paper, they analyzed the traffic from 2 test beds in the United Kingdom and in US. So they observed that their traffic sometimes differs. For example, devices in US generate more traffic or connect to more destinations. So they explain it with this might be due to different privacy regulations in different countries. So basically what we try to say that smart speakers, for example, deployed in United Kingdom and the US, that amount of traffic that they generate might differ, and this might impact the performance of the models. You know, so if the device was trained on US and if the models were trained on device in US and that model is going to be used in device in UK, they might need retraining or reselecting the features. So this was a thing that we didn't analyze yet, and this might be interesting work to do in future. So
okay, so that is sort of regulation driven. Do you think there's a danger that it could change quite often?
Yeah, actually, so yeah, I mean, so basically that was a paper that I read and it grabbed my attention. So I just want to mention it as a future work. This might be interesting direction to follow.
Okay, thank you very much. Does anyone else have any other questions for speaker number 1, paper number 1? Okay, then it seems we can let you off the hook and you can go and retire. Thank you very much. Sorry, let's move on to paper number 2. So is there anyone present for paper number 2 that we can discuss with? Please show yourself and get ready for some questions. Hi.
Hi.
Hello. Right, so we do have questions for you. So the first question comes from Slack. There's one question that's just asking if you can elaborate a little bit on the capabilities of the attacker that you use for this work.
So just more like general question and problem in this paper. So we are all talking about any anomalies happening in the IoT network. So an attacker can have a scan attack, scanning for the vulnerabilities for any compromise for the IoT devices. And also it could be some flooding attack. So our approach can apply to any kind of attacker. So attacker can, any kind of anomalous behavior is happened, then we are able to detect them. So that is basically our goal. So when you talk about the capability of the attacker, I will say is more like any kind of floating attack, scanning attack, DDoS attack, that kind of things, which they are trying to destroy the IoT network. Yeah.
Okay, thank you. So maybe as a follow-up to that, and maybe a general question on anomaly detection and IoT in general. It is slightly different because you talk about edge nodes, and edge nodes generally are not very secure devices, and they're sort of sitting out in the public, right? So how important or how difficult is it to allow for them to be compromised? Because if we have a doorbell or we have a camera and the attacker compromises it, how easy is it for people to manipulate system-wide anomaly detection mechanisms then?
Yes.
So is it possible, or is it quite a hard problem? Well, it's an interesting problem, but do you think it's a solvable problem or not a solvable problem?
We're talking about this because I'm not sure, like we talk about, we have the central node. The central node is in public, yes, I understand, but the central node here, I'm more talking about like for a smaller scope, you can be the gateway in the central node. It can be also like central node. And more bigger scope, you can say the central node is a cloud service, like AWS, this kind of central node.
Yeah.
So because feed learning can apply in different scope. So whether it's in a IoT or whether in a different organization or different countries. But I think it's interesting things to think about. Yeah.
Okay. Anyone else have any questions at this stage? No? Okay. Thank you very much. Thank you for your contribution.
Thank you very much.
Okay, so let's move on to our last paper. So LightningStrike. We have the author here.
Hello, can you hear me?
Yes, we can hear you.
All right. Hello.
Hi.
Thank you for introducing me.
Yeah, no problem. Okay, let's move on to some questions. So some questions from the Slack. So did you consider automated analysis of the structure of the frames transmitted by these IoT devices? For example, the various types of frames, their fields, and whether encryption was used, etc. Anything like that?
So we definitely considered fuzzing and other methods of figuring it out. However, we wanted to go to the bare basics, see what we could do with the basic, just injecting messages, doing the basic attacks without any form more complex. I feel there's definitely more room to add on this. We just want to prove, first of all, that this is even possible in the first place, and then we can jump on to doing more complex things, basically.
Okay. Okay. I hope that answers the question. Right, moving on to the next question. So what do you think is the core problem in fixing the vulnerabilities you found? So is this something that could basically be handled with existing security crypto mechanisms? Or do we need new IoT methods to develop? So to the person asking the question, it seems more like an incentive on the developer's part not doing it properly than a technical challenge.
So this is a and thank you for the question. There's a couple of different problems here. First of all, yes, there might be algorithms that are right now, encryption algorithms that will work to defend against these type of systems. However, the problem is that these systems are already installed everywhere and they want backwards compatibility. So how are you going to have backwards compatibility, but then put encryption on top of things? And even if there is encryption for some systems that are not E-IoT, sometimes they make it optional. So people may not even put it in the system because they lose the backwards compatibility. So it is a problem. Probably should come with new versions. I feel like maybe some vendors are trying to move away from network buses and maybe try to move into network, but I haven't seen it. These devices are still very common. I actually have the devices are here next to me to show if needed to.
Okay, so maybe I can just, sorry.
Yeah, I hope that answers the question though.
Okay, I have a quick follow-up to that one. So,
yeah.
So when you were looking at what these systems were used for, I understood that the proprietary algorithms come from developers that say, okay, the standard thing is not good enough, so we're going to add some things onto it. And then it seems to be used for things like building automation. So in some industrial systems, security is tricky because we have quality of service, we have very strict timing constraints. In these systems you tested, do you think those constraints led to security issues, or is it just, once again, the security just not being there?
Well, these systems have existed for a while. So they're using technology, they're using the protocol. I don't know if they have done many updates, but the protocol has existed since I started working with these type of systems. That was like almost 10 years ago. So I think they may be using the same protocols from way back. The company actually Crestron started in I think it was either the 70s or the 80s. So they've been doing this for a while. And all of the companies that do things like this, they've all made their own proprietary protocols. They have keypads and they follow the same daisy chain design that goes from keypad to keypad to keypad and to devices.
Okay, that's fine. Okay, so another question coming in on Slack. So what is the entry threshold or the complexity for the attacker to execute this? So in other words, how are the messages injected? Does he or she need specialist control hardware? Does he need to get on the bus? Or how does it do it?
So it does require physical access. It is a physical bus, right? So I brought my spaghetti of network bus right here. And I actually bought a USB to RS-485 because it's based on RS-485. So just a USB, the difficult part was finding the details of the protocol because I had to go online. I had to search, we had to search through manuals and manuals and manuals to find out the proper configuration of the port. And then once we connected, we did start seeing messages. So I have another one right here to show. This is actually the test bed on the picture. I know it probably looks bigger on the picture, but it's right here. So all the communication between the devices is actually through the same communication bus. So we have power controllers, and as far as the cost, it is cheap. Those, unless you fry one, which I did by accident, it is $30 for one of the little connectors to actually connect to the bus.
Okay. Yeah, but I think so. But like connecting to the bus, if it's like a building automation, it's so easy, right? You should be able to find the wire, right? I
mean, you go to, if the thing about these systems, these is for example, the one I have right here is a lighting control system, right? So it controls all the lights in a building. So if you're gonna have a building that's controlled with this type of automation system, all the lights or most of the lights need to be controlled through the system. That means that they're gonna have to have those keypads in each room, in all of the rooms, because otherwise how the loads are controlled in a centralized area. So the thing about that is that you will be able to find a bathroom or a conference room or a place anywhere that you could take the keypad, connect your thing, put the device in, leave your keypad inside. That's it.
Okay, thank you. Does anyone else have any questions? Last opportunity. Oh, I think we're good. Nothing else coming in. Thank you very much.
No, thank you
for that talk. Thank you. Okay, so that concludes our session. Thank you for everybody for attending. Special thanks to all our speakers for the nice talk and also the Q&A answers. And thank you for those of you that put questions on Slack. It's always nice to get some help thinking about questions for the speaker. And I think we're almost on time. We're 1 minute early. So I thank everybody and I conclude the session and enjoy your break. Thank you.
So welcome to the first keynote presentation of our WiSec conference. It is a great pleasure for me, and I'm excited to introduce our first keynote speaker, Stacey Higginbotham, who was actually recommended to us from within the WiSec community. Stacey Higginbotham is a tech journalist and a publisher of Stacey on IoT, which is a newsletter and a podcast and a website around the topic of the Internet of Things. She founded the publication in 2016, 5 years ago, after having worked for publications such as The Deal, Giga Alm, and Fortune, where she was also a senior editor. She has spent 2 decades covering technology, and she is also a big fan herself on IoT in general. She will be joining us now from Seattle at this moment. And while not being a security researcher herself, I'm particularly looking forward to hearing about your perspective, Stacey, and what you will be telling us to us researchers, basically, based on your past work in the field of IoT. So the stage is yours. Can you try to put on your slides? Yes, your video is there, and slides are coming, I think.
I hope y'all can see my slides. Good morning, evening, afternoon, everyone. And my name is Stacey Higginbotham, and as she mentioned, I write about the Internet of Things. And I am really excited to be here and also a little bit nervous because I read tons of research papers on privacy and security because it's such a crucial aspect of the IoT. So I just want to get started with this presentation. I hope y'all enjoy it, and I hope afterwards it generates some really good discussion and questions. So let's get started on living a life without secrets, thinking about privacy in an era of IoT. I start all of my talks off by explaining what the IoT is. I know y'all know, but let's all get on the same page. So we've got cheap sensors everywhere now. We've got ubiquitous wireless and not just cellular or Wi-Fi. We're putting out low power wide area networks, which means those sensors can be anywhere and communicate back to either a phone, a gateway, or the cloud, where we also have really cheap computing that is accessible. So what we're doing is we're building this physical infrastructure of data gathering devices that then we can do cheap analysis on. This is going to be what I think of as the body of the future. And the soul is going to be AI. So all of this data is going to be coming in. We're going to be doing analysis on it. Maybe it's not all formal machine learning and AI, but a lot of it will be. And this means that there's going to be computers in almost everything. And computers won't even look like computers. And so that creates a whole series of challenges around privacy, security, data access, and we're going to have to come up with a bunch of new solutions to deal with this problem of like invisible computing everywhere, pulling our information, seeing the data that we leave behind us, and making all of that data searchable. So the types of things we're going to be talking about towards the end of the presentation are going to be ways to solve that with regulation, ethics, and different research areas where we still don't know kind of what we don't know. So let's start with privacy. I like to start this off with kind of just some conceptualization. So we start with privacy. When you walk into someone's house today, you might be in the position or in the presence of a Madam A. I call it Madam A. It's an Amazon Echo, but I don't want to set anyone's Echoes or Googles off. So I call them Madam A or Hey G. So you might walk into someone's house and there could be a smart speaker just listening in, hanging in. I know that they're waiting for wake word detection, but we also know that that's not entirely accurate yet. There's lots of false positives happening. You also might be on camera, and we haven't really established rules yet for how comfortable that might make people feel, what kind of disclosures we should have around that. And these are social things. These are not necessarily technological solutions. I also want us to start thinking about what it means for our families when we put these devices in our homes. My favorite example is we have this oven. It's a June oven. It's a smart oven. We love it. It's connected to Wi-Fi. It has a camera. It shows you what's cooking. And you can also put an app on your phone. Now, when I put the June oven in our house, I connected it to Wi-Fi, but I didn't download the app because I didn't need to look at pictures of my food while it was cooking. But my husband decided to. He didn't tell me. So one day I'm ready to go to actually another talk, and it's in the morning. And before I go, I'm like, oh my gosh, I need waffles. So I'm gonna eat my waffles on the road. I put them in the oven. I hit the button to toast it. It dings. I grab my waffles and I'm out the door. But then my husband calls me and he's like, what are you still doing at home? Why are you making waffles? You're supposed to be at your speech. And all of a sudden I realized this man has the ability to spy on me based on what I'm cooking. And my husband doesn't really care if I'm eating waffles 24/7. But now I know that he knows, and it was kind of an icky feeling. I also know when my daughter's baking chocolate chip cookies, which is kind of handy. He could come home if he wanted to when he saw that happening in the oven. So that's just something to think about, right? From a privacy perspective. And then the other thing to think about is when you have these computers everywhere, it becomes really hard to implement security on some of these devices if the security is reliant on the user entering passwords or kind of more common things. We're getting away from that with QR codes, and thank goodness. But I always leave this picture of like the first generation Nest because I remember having to implement my 28 character password on this dial Nest thermostat, and it took me forever. So just thinking about usability when it comes to things like security on these devices is worth thinking about. So let's talk about privacy. Basically, when you set up a smart home or sensors in your office, you are creating a surveillance network. And it's possible in public, in homes, in your offices. And what I've got here are some examples of people doing this. So this little lanyard badge is actually deployed in certain hospitals, and it's to check if people are washing their hands. It was deployed first with nurses and then later on with doctors. But this tag has a sensor that communicates with hand washing stations, and basically it offers a record of who has washed their hands and where and how many times per day. Now, this is a legitimate public health use case, but do not be misled. This is surveillance. And so what are the rules when you're saying, hey, public health, how do we communicate this? And is it right for us to be doing this? Think about things like, hey, can this lanyard figure out if you're in the bathroom? Well, I mean, you wash your hands there and you might want to know if your doctors are, but then you know they're in the bathroom. These are kind of questions that people who deploy these solutions need to be asking. And I would say people who build these solutions need to be thinking about. In the home, we already mentioned the digital assistants and walking into a home and having those there. And then the bottom thing is in public. This is facial recognition cameras in China that are detecting people's temperatures and pulling out data on who's running hot. This is a COVID tracking mechanism. Again, there's a public health rationale for this, but how is this communicated and how is the AI tested? There's a lot of questions here around privacy. And the backlash is here. People hate this stuff and they get very upset when talking about it. So we think about things like Ring's Neighbors app. And what this is when you Ring doorbell cameras and security cameras people have put them everywhere. And Ring started a marketing program with municipal police organizations. And what they did is they basically said, hey, if you market our device, we can also get access from this footage to help you solve crimes. This sounds really innocuous, but what happened was it's turned into a privately owned public surveillance network. During last summer, when the Black Lives Matter protests were happening, police in LA actually called for and requested data from Ring and other video doorbell camera networks in the city to find images of protesters. This runs afoul of a lot of civil liberties and definitely a lot of privacy concerns. We also can talk about China's tracking of people during the coronavirus outbreak. Again, public health, but then you look at what's happening with the Uyghurs and you think less public health, more, hey, public surveillance and control of a population. Another example of this is the Daily Telegraph, a newspaper in the UK. They deployed occupancy sensors under desks throughout their newsroom. And reporters found them and they said, hey, what is this? And being reporters, they looked it up and they discovered that these were occupancy sensors. And they realized that their bosses were tracking them and nobody had told them. And obviously, if you think about the relationships you want to have with your workforce, this is not an ideal situation. We could also look at the backlash right now in all of Apple's marketing strategy. If you were part of the WWDC event just a few weeks ago, privacy was front and center, and people are buying it. Whenever I talk to people about privacy now, they're like, man, I'm dumping Madam A, I'm getting Siri, I'm doing all these things. And we can talk about the subtle gradations of privacy later, and we will, but this is a big thing for a lot of people. We've also got legislation around privacy happening. Okay, so how do we think about mitigating these harms from having basically a surveillance network everywhere? Companies should be looking at their data collection policies. They should be thinking, hey, what data do we have? What data do we need to have? And what data does our partners have? How long do we need to keep all of this data? Do we even need to keep all of this data? One of my favorite companies, they're no longer around, but it was a smart doorbell company. And they said, hey, you know what? We're going to use your Wi-Fi SSID and password. We're going to take it and then we're going to dump all that data because we don't actually need to know that. As opposed to a company like LifeX, who when they launched way back in the day, they actually transmitted your Wi-Fi data and your password in plain text over the air and then stored it in an S3 bucket that was not secured. And yes, people found that data. So start thinking about things like that. And we also need to think about how to communicate that with people so they feel secure. And then most importantly, or not most importantly, also importantly, what sensors do you have? What do those sensors know? People in 2019 got very upset at Nest because Google, because their Nest Secure security system, Nest introduced a new feature that would listen for glass breaks. Nest was thinking, yeah, we're awesome. And then everybody suddenly was like, wait, I'm sorry, you what? You have a microphone on this thing? And that sort of communication needs to happen. And we have a lot of really good research happening around this. So we've got Consumer Reports is starting to publish reviews based on this, like knowing what kind of sensors are in things. Carnegie Mellon's computer science lab is doing a nutrition label for data and privacy to be placed on these devices that talks about disclosure. Google, after their whole debacle, started printing and posting all of their sensors on the website. So there's a lot of movement for mitigating some of these risks. We also need to look to laws, and we'll talk about what those laws might look like towards the end. And we also need to have real public conversations about when we should be doing surveillance, when we should turn on the surveillance capabilities of the IoT, and when we should not access them. So things like a missing child, maybe you do use facial recognition to try to find the person who grabbed that child and find them quickly. But maybe you don't use it for just tracking jaywalking. These are the sort of conversations we need to be having. And right now, our conversations are very black and white. They're like facial recognition, bad. Privacy, good. And that's not how this is going to work. You can't have a binary surveillance network. And we need to talk about security practices that actually work, because as someone who has 60 some odd connected devices in my home, thus I have 60 some odd accounts with data about me and my family located in myriad places on the web, security, good security is privacy. any one of those accounts gets data leaked, all of a sudden I've got hackers having access to Lord only knows what. So let's talk about security. Okay, exciting things are happening in security. Ever since the Mirai botnet from 2016, everybody was like, oh, we're bringing all these devices online and they are not secure. And that's not a great thing. So we started getting serious about it from the consumer side and from the industry side, but we are not far enough. On the consumer side, people email me every day with the following two questions. Question one, how can I separate my IoT devices on my network from my important devices? And the answer, honestly, is yes, you can set up like a really intense guest network with using ubiquity and like do all these firewalls for accessing, letting different devices access other different devices, but it is a process. It involves a lot of expensive gear. And most people aren't going to do that. So what they do is they try to buy these Bitdefender, firewall devices that are tracking their traffic, that sort of thing. Is that ideal that consumers have to spend another, it's between 200 and 500 bucks on these devices? I don't think so. There's also things like multi-factor authentication, and it is surprising to me still in 2021 how many of my devices that control things like, I have something that controls my water in my home, and it just got multi-factor authentication. So for the 3 years that this device existed beforehand, it didn't have it. And someone could actually, turn my water on and off in my home. There are still devices that don't have multi-factor authentication that have that sort of risk profile. And then we also have really forward-thinking things happening at the industry level, such as ARM's confidential computing initiative to help with securing data in computing data in secure ways. These are not things that consumers are going to have to care about, I hope, but they're there. So let's divide our security chat into security by professionals. TPMs and secured computing devices, thank goodness, they are now like not just being used, but they're actually, the software in devices are coded to take advantage of them. This year, I thought it was really significant that we saw a 32-bit MCU with a secure hardware root of trust on it selling for $1. This is great. This is making security cheap and accessible for everyone. Encryption is becoming more and more common. We're seeing not just data at rest, but data when it's traveling. Our camera data is being secured. This is all really important, and consumers are asking about it. We're also seeing companies address their vulnerabilities publicly, and they have bug bounty programs. And I think this is really important. Like 5 years ago, when people were asking me how how they would know if a device is secure, I would be like, okay, look for the over-the-air updates, look for bug bounty programs, Google the name of the company and make sure that they're addressing vulnerabilities when they come up. And I can tell you, just based on my email box, when some sort of big vulnerability happens now, I no longer have to call these companies and I'm like, hey, what are you doing about it? Instead, they're proactively coming to me and they're saying, hey, just to let you know, we're going to have an update for this by, in a week. So please tell everybody. So I think that's a really important step that's happening. We also have innovations like Azure Sphere. So trying to have device to cloud security for all of these things. We're also doing network monitoring in the consumer world, in the enterprise and professional world. We're seeing a lot more companies deploy things to understand that they need to know exactly what's on their network and how it's behaving. That's becoming very standard. And security certs and recertification of those certs every year are becoming part of standards. And this is so crucial. And I'm so excited about this. We've got things like UL obviously has their UL bronze through, platinum, titanium, their 5-level security model for IoT devices. And all of those have to be recertified. Sure. Do I think it's great that UL bronze sounds really good, but it's really kind of lame? No, but I think it's important that that's there. And then we also have things like Matter, the upcoming smart home standard that used to be known as Project Chip. This has a really innovative security model, and I'm super excited about it because it actually ties into one of the big open research areas for IoT security. And that is, they have created a distributed ledger for tracking each device that is Matter certified. It tracks the device, where it came from, the updates that it's currently had, like its software version, any updates as they come through, and they can actually track a lot of other things. Matter also requires encryption to be certified and requires a device to have over-the-air updates. But what's super cool about this is because this is a distributed ledger, it's a blockchain-based way of handling security, we're looking at a programmatic way to check those 60 some odd devices in my home. I can have a service now that checks that so I don't have to manage it. And that's great because consumers don't manage their stuff. You want to know what else? You want to know what else consumers don't do with security? Ooh, we still suck at passwords. Only 33% of boomers, and I think it's 28% of millennials, actually use new passwords on a regular basis. We are so lazy. Only 21% of users implement 2FA, according to a HelpNet security article. And that's on the rise, but still, y'all, it's 1 in 5 people are using 2FA, and the rest of the people, and some of those people are still going to be using password as their password. Consumers also don't understand risk models. They don't understand that their camera data, or maybe their HVAC system, or their smart water system that can turn their water off, has a much higher risk profile than maybe a pair of smart socks that just tells them if they're pronating. And yes, that exists. I have them. So consumers just think security is an all or nothing thing. And I don't think it's reasonable to expect them to be too much more sophisticated about that. And a good example of that is cheap still trumps security when people are purchasing things. 1, it's because it's cheap. 2, it's because security labels are really hard and confusing. Colin Engel, the CEO of iRobot, told me that when they put security labels and data on their boxes for their Roomba devices, consumers actually passed them by because they felt it was too confusing. So they had to stop. He's actually a big proponent of sharing this information, but consumers don't want to think about that when they're buying a device. They just want the instant gratification of buying their Roomba. And consumers hate to update their software and manage this sort of thing, which again is why I think those Matter certifications that could be programmatically controlled are so interesting. So let's think about security and privacy in terms of all of the data we have. I think of this as data exhaust. That is data, metadata, everything about you as you move through your life. So I think there's 5 layers of sharing. I envision this like a bullseye, concentric rings. There's the individual, that's just me, my household and family. Remember that June oven example? We got to think about those people. There's the manufacturer who's making the stuff, providing the app, doing the algorithms, etc. There's the third parties affiliated with the manufacturer. And there's the potential for governments to have access to this. So let's talk about each layer. Individuals. On the internet, our data defines us. We are demographically sorted into categories that can be very granular. But in IoT, I maintain that data can confine us because it can much more accurately identify who we are, who we spend time with, and where we are in time and space. That's very scary. That is unprecedented. I don't care what people say about, oh, this isn't surveillance. This is surveillance. If we want things like personalized medicine or a really accurate digital assistant, something, someone, somewhere has to know an inordinate amount of information about us. And people don't realize that. For a long time, this has been the end of personally identifiable information, and yet our laws are still predicated on this archaic concept of my name, my address, my social actually mattering. That's protected. But the fact that my geolocation from my phone isn't, that's a problem, and we need to talk about that. We now have the beginning of personal graphs, data graphs, and social graphs. So it's not just me I might be implicating in something, it's the people around me. We have these webs of relationships to things, to other people, to places that are now very clear, very searchable, and as of now, stored forever, and not always stored very securely. Opting out is not going to be an option for long. People love to tell me, oh, Stacey, I don't care about all this. You're so stupid for having this stuff in your house. Just don't buy it. And yes, that works for some things for today, but most people have a cell phone. Most people have their location on that cell phone. When we add smart cars, many people are going to have smart cars, which has all of this sensor and tracking potential. Same thing with appliances in the home. In about 5 years, I don't think you're going to be able to buy a home appliance without some sort of smarts associated with it. Same thing for HVAC and thermostats. So not everybody has to install a Ring doorbell camera, but people are going to be bringing these devices that have sensors and tracking abilities into their home. We also see it on medical devices. And at the individual level, security and privacy is impossible. Everyone should internalize that. It is unreasonable to expect an individual to be able to assess all of the terms and services, to understand everything that's happening, even if you shove 1 million very well organized data labels, like nutrition style labels, in their face. It's just not, it's not going to happen. And we should stop blaming the individuals for these issues. Household and family. The number one thing I want you to take away from this is home is not a safe place for everyone. There are people who are being stalked. There are people who are in abusive relationships. There are even parents who just have really crappy boundaries. I used to ask people at big talks when we could all raise our hands and I could see when we were talking about privacy, I'd be like, hey, how many of you have children? Hands would raise. How many of you used a video baby monitor? Hands would raise. All right, keep your hand up until I hit the year at which you stopped using the video baby monitor, or you would become uncomfortable using that video baby monitor. I'd say 1, most of the hands stayed up. 2, someone went down. 3, most of them went down. Some people stayed up until 8 or 10. These are 8 or 10-year-old children whose parents are still have a video camera in their room, which it's not abusive, but it is definitely questionable. So we need to have conversations about when you're putting these devices, building them, or thinking about them in the wild, how do you do transparency about what a device knows and what a device's purpose is in the room? A friend of mine, Carla Diana, she's a designer. She talks eloquently about this. She says, you know, if you walk into someone's room and their grandma is sitting in a rocking chair, ignoring your conversation, but you still see her there. So you know that there's a possibility that grandma's listening in, even if she's not. You see her, it's a social cue. But when we walk into a home with like Madam A or Hey G, we don't necessarily recognize that as the same thing as a grandma that may or may not be listening. So how do we think about making their presence visible and their capabilities visible to people who are in the home? Also, how do you get buy-in from members of the home? Like whenever I bring a new device in, I now have a conversation. This gets old really fast, y'all, but I have a conversation with everyone in the house. I'm like, this is a camera. Here's the sensors. Here's where we're putting it. Everyone should know. My family gets irritated, but it's important to me to do that to them. It's also important to me when we don't actually have cameras that face inside in our house, except when we go out of town and then we stick some in. If anyone comes into my house and I know they're coming into my house while we're on vacation, I let them know in advance there's cameras there, because it's important for me to say, hey, you may not expect a camera in this house, but there is one. And I think that should be I don't know if it's a social convention or it should be regulated or how. And then we get to the next concept. Sometimes you don't want your data tracked. And I'm not thinking about like you're out murdering someone. I'm thinking about maybe you're just having a bad day. You don't want devices trying to algorithmically figure you out. My friend Mark Ralston, another designer, has this idea of creating digital cloaks of invisibility. And he has no idea how this is going to happen. Maybe it's a little like a cell phone jammer style device that you compress. Maybe it's just a command for Madam A in your house, just turn it all off for a minute. But having something like that feels like it's going to be important, especially since we can't opt out. And then for your household and family, policies and standards that promote security and privacy are necessary. If you're making a device, you need to think about these, I want to say they're edge cases, but unfortunately, some of them are not. There are a lot of people living in abusive situations. There are lots of people who are weird stalker type people, and given the tools, will try to use this to track people. And maybe it's not even malicious. Maybe it's like me. I am really excited about the holidays and I love presents. So around the holidays, we have a Tesla. So I can look on the phone app and I can see where it is. And my husband has to remember not to take that car when he's shopping for my presents, because I will actively look on the app to see what stores he's at so I can try to figure out what I'm getting for Christmas. So again, not malicious, but he'd probably like that digital cloak of invisibility. Barring that, he has to think about changing his car. I know y'all are like, why is this man still with you? At the manufacturer level, think about the data, with the data that they have. Between me and the manufacturer, we definitely need clear data sharing policies. I want to know exactly what they can get from me, and I want to know what they're doing with it. They also need to think about things like privacy by design. If you are installing a camera in a house, do you need to? Could you use something like fall detection instead of a camera? Could you use radar? These are the kind of questions people need to be asking. We talked about this. How long do you keep that data? And what certifications should I get? How stringent should they be? I would advocate for super stringent, but I am a consumer. And then manufacturers also need to think about the risk profiles associated with that device when they're thinking about building it. So is it a camera? Then you should be encrypting that data. You should probably also not have, then you should probably also in your app have little warnings about, hey, someone has joined this account so they can see your data. Those kind of things need to be part of any design discussion as a manufacturer. Let's talk about third parties. The Internet of Things is not actually an internet of hardware devices that are connected to each other. It is so much more complex. The Internet of Things is actually a bundle of software in a hardware device that has maybe from a dozen to 100 different services behind it. So basically, the Internet of Things is hardware blobs that have these many tendrils of interlocking relationships. My light bulb, my light bulb has a communication back with the cloud. My app for that light bulb might have a dozen communications back to like analytics sites or tracking sites, all of this. So your third party security matters. And this can't be as simple as, oh, yeah, I like this cloud, or I like this, I need data analytics. This guy sold me a great package. You have to evaluate how they store that data, what they track. Their API strategy matters because it'll break your hardware blob if something happens on that end. Their data retention and access should be limited. You need to ask yourself, what data do these people have access to and how can it be used? I'm not saying you have to tell the consumer, although I think you should have a website with plain text language about all of this that they can access. But you need to know, because this is a weak link or a potential weak link. And what we know about security is it's just basically plugging in the weak links, knowing what they are and plugging them in as they fail. Manufacturers should conduct annual audits to review these policies. So Google has started this with being part of their Works With program. I even think retailers should have these sorts of audits with their partners as well, because they need to, consumers can't, like I said, they can't do this. We need to have people who are responsible for these devices check that all of the inputs to them are behaving like they should. And if that sounds like a freaking nightmare, it is. And that gets to one of my favorite points here of research. We don't have it yet. We need to find ways to scale data use contracts automatically. Just like we have the digital ledger as part of, or distributed ledger as part of Matter, we need to think about how we can contractually control access to consumer data and make sure that the people who have access to that data are abiding by those contracts. And that is not a human job anymore, because we have so many tendrils and so many interlocking agreements. Right now, we're building out IoT physically and working on all the computing problems. But in the next, I'm going to say 5 to 10 years, it's going to become a legal problem. It will become all about these sorts of contracts and maintaining them. And speaking of government, we've got to ask what data government can get from personal devices. People don't think about this, but my geolocation data on my phone is only a subpoena to Google away. And yes, there's a subpoena, but we actually don't have an understanding yet about what government can access, what police departments can access, and how that can be used. And we'll talk about that as a solution to that problem in a bit. So we need to know what data government can get from public devices and when they can implement things like facial recognition and when they can't. So what situations merit a breach of privacy? Because again, that is what it is. You're going to breach a bunch of people's privacy if you suddenly start using facial recognition to track people on public streets. I know they're in public, but it is a very different concept than having a person who doesn't have infinite memory to having a computer do this, because they can recognize you, they can tie you to that place, and then that place becomes searchable for potentially all of time. And that is frightening. And what situations, and what rights do we as consumers and individual citizens have to shield our data exhaust? The courts are still figuring that out. We get court cases all the time about things like sticking GPS on cars. Can police officers go on like a fishing expedition and grab all of the geolocation data for phones around an area where a crime has occurred? We don't know yet. And it's really scary running around in this world not knowing that. And then can our daily data exhaust incriminate us? We've already seen Fitbit data. We've seen water usage data. We've seen smart speaker data be pulled into criminal and civil trials already. And it's going to take us years to figure out, is that data admissible? I don't know. So here's the fun part. What do we do? Sorry. So what do we do? Principles of regulation for the IoT era. I would love to have us define consumer rights for what is essentially software designed as hardware. And this has it has implications for privacy and security. So things like, hey, put an expiration date on that device so we know when it stops being useful. But some of these are just like nice for consumers, but I think it's important to do. We need to rethink the Fourth Amendment for a digital era. The Fourth Amendment of the US Constitution is against unreasonable search and seizure. And yes, this is a very US-centric talk, but the EU also has rules around this that we can talk about. But the idea here is we can't stop this data collection. We can't control it even. So now we need to start having conversations about when people can access it and how. So if the police go to a company, or if a government goes to one of these third party, like not even Google, but maybe one of the third parties that Google contracts with for data analysis, If the police can go to them and buy that data, then is that fair? Is that a good use? Is that something we want to have happen? We need to start having those conversations. And right now we're not. We're having stupid conversations about facial recognition's bad. Just ban it all. That's not what we need to be doing. We need to be thinking about, if this data is out there, how do we define our rights around people who can access that data, what that data can be used for. And this is not just for like law enforcement. This could be everything from like health insurance. Can you get health insurance if you only walk 3,000 steps a day? I don't know. We need to talk about that. We need to put laws into place that penalize private entities for leaking data. And this can be unintentional, but we need a bigger stick to make them really invest in security. And we need to require rapid disclosure. So hackers are getting much more active. They're much more on top of things. So when these vulnerabilities are disclosed or someone's data has been leaked, we need to give people the tools to address that quickly. We need to build auditing authority into existing government agencies to test AI outcomes. I know this feels like it's coming out of left field, but the bottom line, again, from all of this IoT, is to create a physical layer to generate better insights around whatever we want. Maybe it's eating better, maybe it's boosting productivity, maybe it's reducing carbon. But we're building all of this stuff because we want to have computers take over some of the cognitive load of managing things. And so when we give them that data and start writing those algorithms, we need a way to have an impartial authority test those algorithms and make sure they work as intended. And this is beyond simple bias, because everything is going to have bias. We need to talk about the policy goals that we're trying to create and bias those algorithms to meet those goals. And we're really bad at doing this. Politicians are bad at talking about this. Humans are really bad at understanding this, but we need to do this. We need to provide GDPR style rules across the world to help consumers control their data. And this is and we need to ensure that data can be corrected. I also want to throw this out here because it's controversial, but I think it's really important. We need to give kids the right to expunge their childhood data. I don't know if it's 13, if it's 18, if it's 25, when your brain finally is fully formed and you stop making stupid decisions. But I think it's really important to let people make mistakes and not have it be searched forever. We can do carve-outs for public figures, but this is just my thing. And we need to rethink current forms of identity and create new layers of identity. And by this, I mean that right now we have our names, we have our emails, we have our phone numbers, and we have social security numbers, and then we have maybe fingerprints and sometimes face prints. That's a lot, but we don't have any rules about what you use when. And the problems associated with that are, when you have some of these get out into the world, it's very confusing for the user to control that. And some of these things should never be out in the world. Like the fact that social security numbers have become a default identifier for people is just a crying shame. And I would hate for that to happen for something like fingerprints or, I don't know, iris scans. So we need to have a conversation about how we identify people online and how we want to use that, especially because we're going to be talking about this, implementing programmatic layers of security. These I'm not going to go into too much because it is the 7 rules for designing ethical connected products. So y'all can read them. Hopefully you get the slides after this. We've talked about almost all of these things. This is what I would like to see in some of that regulation around the regulation for having our hardware basically be blobs of software. So y'all can check that out. And then I'd like to end on the areas that need innovation. This is where y'all come in. We need scalable security for connected devices. I don't know how we're going to do this. I want to see as many options on the table as possible. we also need the same thing for data contracts. We also need incentives to help consumers accept things like multi-factor authentication until we get those better digital identities. Y'all can research that too. Oh, it's on the list. So research around how to make basically secure interaction with computers everywhere viable. And then finally, how do you solve a problem like ancient gear? One of the biggest security challenges we face is we have all of this old gear that doesn't have like trusted computing modules or secure hardware root of trust on them. And I don't know how we're going to get this gear out of distribution. And we need to solve that problem as well. So that was a lot, but I'm hoping y'all have questions. You can ask them now, or you can reach me at @GigaStacey or Stacey at StaceyHigginbotham.com. And I would love to have this conversation with y'all.
Thank you very much, Stacey, for this great presentation. It was wonderful for me to see how it unfolded, and there were a lot of points where I nodded while you were speaking. So I generally like the idea of the layered approach of looking at the privacy questions, of not making users responsible, of ideas you put out like promising users for how many years their devices will work, allow people to make mistakes and not be kind of have that searchable for a long time. So where there were a lot of great ideas. We will have questions, I guess, that come in, but let me maybe start with first questions from myself while I'm still collecting questions that are coming in. And I would like to motivate everybody who has questions to just put them out on the Keynotes and Awards channel on Slack. So please write it down there and I will come to that in a moment. So I wanted to start off with a very short question. It's a technical question, actually, that I was thinking about at the beginning of your talk. You showed this device for like this hand washing sensing device with a picture where you could figure out when people have washed their hands and when not. Could you give me a very short idea of how that works? Because I was really, I've never seen it before, and I was just wondering, how does that actually work? What's the idea behind that?
So one of the stopping the spread of infections in hospitals is a big issue. And I can't remember who makes that particular device I showed, but in general, these devices in Stanley's hospital unit makes them. There's a bunch of other companies. I think J&J has a similar situation, but you get a lanyard. Everybody who works in the hospital interacting with patients has this lanyard. There is either a Bluetooth radio or it's RFID based. I don't think it's usually RFID based. Some of them are actually. And what happens is when you are at a hand washing station, it tracks that you've stood there basically for X number of minutes, seconds, I guess 30 seconds. And so you could fool it by standing there and not washing your hands. But the idea is you wouldn't. And then it logs that and then you can audit it and that sort of thing.
Okay, so it's about the proximity of you being close to an environment that enables hand washing, basically. Okay, I see. I got it. Got it. Okay, thanks. We got a question here from Florentine. The question regards passwords and identity. And the question is, what do you think about authentication tokens like YubiKeys or FIDO2 or web authentication standards? Have you thoughts on those?
Yes. I mean, yes, I actually have a YubiKey. And specifically for consumers, I mean, the types of devices we're thinking about securing it's not helpful for that. Now, the FIDO Alliance has come up with a standard for enterprises that secures devices coming onto the network, and it does a lot of like the attestation work, and it is a standard that they announced 2 to 3 months ago. So I'm generally in favor of those. I don't know what else to ask or how to else like what else you want to know about that.
The question was not more specific than that, but just by you saying that you're using them yourself, that says something.
Oh, but okay, but so I am not a normal person. No one I know, I mean, none of my friends or family, okay, that's not true because I have a lot of technical friends, but my non-technical friends and family, they do not wander around with like a YubiKey or a Titan security key. And the other thing is, you know, every time a news story breaks about like, oh, Google's Titan security keys, I think there was a Bluetooth, there was some vulnerability associated with some of them. And then everybody was like, oh my gosh, those are so insecure. And they don't make the distinction between like the individual devices or the fact that Google stopped producing those. That's a problem. Because again, people they don't want to have nuanced thoughts about security. They want it just to work. So I don't know, that's more detail.
Thanks, Stacey. I got another question. I will read it out in a moment. Let me just say to everybody, if you feel you would prefer asking the question directly by turning on your audio, unmuting yourself with or without camera, just raise your hand and you can also do that. So we do not have to go via this, me reading aloud the questions you are writing. You can also say them yourselves. Just please use the raise hand function so that I can see you and we can unmute you. So a second question that we got is what actually speaks against just using less IoT? So it does not need to be IoT just being available, being able to use it does not mean that we necessarily need to use it. So the question is, what speaks against just using less IoT as long as it's as insecure as it is right now with all the security and privacy implications that you have outlined. For example, just not buying smart cars as long as there are still non-smart cars available. So I just read aloud a little bit further here is it seems you were saying like in the future we won't be able to buy washing machines without IoT. As well as have 1,000 IoT devices right now. So I guess the question is, what can we do from that perspective if we as users don't buy all the devices that are there?
Okay, so again, I have a lot of thoughts about this because I am fundamentally optimistic about technology and using technology as a tool that can really help us solve a lot of our current issues. So I think IoT is incredibly powerful for things like conserving energy, tracking air pollution, being able to, I call it making the invisible visible. And I was thinking about this yesterday and I got really bummed out because I was like, oh, in a capitalistic society, we'll only use it to like boost productivity and like basically eke out every dollar we can from people. But I do fundamentally believe that we can make things like air pollution visible. We can use data from smart thermostats to help people understand where more energy, like where their homes or offices are energy efficient. We could also use it to nudge people into maybe conserving energy by, you know, noticing that they're using way more energy than their neighbors, for example. So I think the positives for society, if we create these outlines, these regulatory outlines that govern how people can use the data, and we create clear policy goals that we want this technology to help us achieve, those are big ifs. I think that's why I'm still excited about IoT. That's why I think we want connectivity and sensors and data from more places, because I think ultimately we can harness that for good. Yes, we can harness it for evil. And I don't think it's a crazy, like, I'm never going to make fun of someone who says, no, I don't want a smart speaker in my house because I don't want Amazon listening in on my conversations. That's totally valid. And I just feel like we're going to be giving so much up, and it's such a potentially awesome tool for helping us solve some of these big issues that I hate for us to leave it behind because it's insecure, because people don't trust it, because we're right now using it for stupid things like selling people more stuff or giving them what I call digital snake oil in terms of like wellness. So we're going down the wrong path, but we could go down the right path. That's just my long and passionate answer. Sorry.
Makes sense. I have one more question to ask that comes from me, actually. You were mentioning a couple of times the privacy labels that could be put on IoT devices, and it reminded me of a proposal that was presented at the IEEE Security and Privacy Conference last year. This was about security update labels. So it was also about labels for IoT devices, but having them for like as an indication of how well supported security updates are on those devices, and have that as an indication if these devices might be vulnerable to attacks. And the privacy label would be could be something that takes on this idea but puts it on the privacy perspective, right? How privacy like how much is privacy at stake when such a device is being used. But if I got you right, and this is actually what my question is about, you don't seem to fully believe in that idea, because it would put too much on, or too much decision, or it would require too much decision power on the user side. Is that what is the main concern with that? Or maybe can you elaborate a little bit on that? Like
Sure.
realizing privacy labels.
So let's see. All right, this is a smart plug box. Just so you'll have it. Right now, this is the labeling about apps and the QR code to join it. This is like things it works with, and so the things it works with are also here. And then this is just like, hey, I'm selling you a smart plug. So the reason I'm skeptical is this is a tiny box. Already there is a lot of information on this box, and to put like a privacy label down here, for example, would be a lot. I think most people in their privacy labels, it's hard to figure out what matters most on a device. And I think it differs based on each device. So if it's a camera, I want to know that my feed is encrypted. I want to know that your employees can't, I want to understand your policies around employees accessing that data. I want to understand, when the microphone might turn on or might not. And I don't think the space for all of that is available on a box. I think it's confusing. I think people, when they're faced with that, they're going to second guess themselves. They're going to be like, oh, I don't want a camera. And maybe that's the right way to do this. I mean, it could be. That's always an option to say, by the way, this is a literal camera that other people could see in your house. But I'd rather see us agree on standards and tie them into certifications. So like the UL certification, like the Matter certification, and then also have access to a website that explains all of these things. Because the other thing is, people say they want privacy. But if I implement all the privacy features on some of my devices that are available, or even on the web, I lose a ton of functionality. Like if I don't let Google or certain apps have access to things, suddenly those apps break. And I don't think people understand that. And so on one hand, we've got companies selling us personalized features like recognize your dog, learn the motion habits of the branches so we don't set off all these false positives. But they don't realize that all of that's going to be based on data that a company has to gather and analyze. And when you give them these privacy choices, they'll say, no, I don't want that. And then they get mad because they don't have access to these features. So there's two things there. One, I think it's just super complicated. Two, I think people, when asked about privacy, as in privacy, they make different decisions when they're asked about the features they want. So.
Thank you very much, Stacey, for a great presentation and answering our questions. There are a couple of comments that are written down right now, but I think we should conclude this session right now. And I would invite everybody who is interested to discuss any of the topics further to join GatherTown. So Stacey will come with us and explore the GatherTown space a little bit with us. So feel invited, everybody, to use the break to just go and meet with Stacey directly. You can talk to her directly. And we will resume this, the next session, so session 2, the second technical session of the conference in half an hour. That will be a technical session on Bluetooth and ZigBee security, so it fits perfectly to the topics that we are talking about here, and will be chaired by Erik Tews. So see hopefully many of you on Gather Town, and the others see you again in half an hour when we resume here. Thank you.
Hello, can everyone hear me? Great. So I'm Erik, and I'm your host of the second session. I'm also responsible together with Merve for the poster and demo session, but now I'm here to host the second session, which is about Bluetooth and ZigBee security. In total, we have 4 papers in the session, one about ZigBee fuzzing, and 3 more papers about Bluetooth. Before we start, would like to say that the videos for the poster and demo session, so we recorded short interviews with all the participants, are now available on the WiSec website as well. So when you're looking forward to seeing the poster and demo session, I think it's on Wednesday afternoon, well, afternoon depending on which time zone you're in, then you can now take a look at the videos on the website, but I would even recommend that you do that not now, but in the break after the session. So let's come to our first video. Our first video, or our first presentation, is about Z-Fuzzer, which is a new way of fuzzing ZigBee protocol implementations. That paper was highly valued by our reviewers because it is a paper that focuses on ZigBee, which unfortunately has not been really in the focus of the wireless security research community, because there you find more papers about 5G, Bluetooth, and Wi-Fi. But this paper took a look at ZigBee, they implemented a new fuzzer, and also they were highly valued for their real-world impact. So they also found real results in real-world implementation. For the question and answer session, Ming-Fai Ren will be here to answer your questions, and he is also on Slack. When you have questions, no matter whether it's during the presentation, during the video or not, or afterwards, then post them on Slack. And now I would like to give the stage to our first presentation.
Hello everyone, my name is Ming-Fai Ren. Today I will present our research paper titled Z-Fuzzer, Device-agnostic fuzzing of ZigBee protocol implementation. This work is collaborated with Xiaolei Ren, Huadong Feng, Professor Jiang Ming, and Professor Yu Lei at the University of Texas at Arlington. With the increasing popularity of the IoT devices, ZigBee protocol has become a dominant wireless protocol to reduce the power and memory cost of IoT devices. It has been widely adopted in home automation, green power, and manufacturing. Recent works have disclosed the weaknesses and vulnerabilities in ZigBee stack implementations. Therefore, it's necessary to detect security issues in ZigBee protocol implementations. The ZigBee protocol is defined by the ZigBee Alliance with various security services that offer a range of options within a ZigBee network. It is a 4-layer protocol stack as shown in this fig, including application layer, network layer, media access control layer, and physical layer. The ZigBee Alliance defines the application layer and the network layer. The MAC layer and the physical layer are defined by IEEE 802.15.4 standard. Manufacturer's application performs functionalities with the commands in ZigBee cluster library. From their perspective, the ZCL is the ZigBee protocol stack's main library to perform all of the device's functionalities. Therefore, we use ZCL as a case study for fuzzing the ZigBee protocol implementation in this paper. Fuzzing is a popular security testing technique to discover software vulnerabilities. AFL is one of widely used gray box fuzzing tools. It can fuzz either source code of the target or the binary file. However, it's not a trivial task to directly apply AFL and its extended fuzzers to ZigBee protocol. For source code level fuzzing, The fuzzers instrument source code and leverage heuristics such as code coverage to guide their test input generation. But such an instrumentation could violate compiler examination deployed in ZigBee source code by the protocol vendors, especially the general compilers like GCC and LLVM used by many existing fuzzers. When the source code is not available, some fuzzers integrate software emulator such as QEMU to emulate the target's binary file execution. Some of them require the presence of a Linux kernel. However, they are not feasible for ZigBee protocol, since it is usually executed in a bare metal system. Though some other emulation solutions also support bare metal programs, currently most vendor-required embedded devices are not supported by those solutions. For example, QEMU currently supports only 2 ARM M3 devices, which are developed by Texas Instruments, but they are not compatible with TI's ZigBee protocol implementation, which is called Z-Stack. QEMU cannot even boot the binary program on the unsupported device. Meanwhile, many black box protocol fuzzing approaches are proposed and developed to generate high-structured packets that conform to network protocol format requirements. However, we notice that they have a limitation on the quality of test input generation. They don't prioritize test inputs, therefore many interesting test inputs are discarded for further fuzzing. As motivated by the above observations, we developed Z-Fuzzer, a device-agnostic fuzzing platform for ZigBee protocol implementation. The goal of Z-Fuzzer is to detect vulnerabilities in ZigBee protocol implementation without the real embedded devices. Therefore, we need to solve several design challenges. First, for IoT device simulation, different devices have diverse underlying hardware, peripheral interrupts, and system configurations. The same peripheral can be configured differently on various devices with different interrupts. It requires significant engineering efforts for the existing simulation platform to add support for all device-specific peripherals and new embedded chips, if not impossible. A good simulator should not consider underlying hardware configurations of specific devices. So, we utilize Simulator from IIR Embedded Workbench, which is an industrial embedded device development toolchain. It's used by many ZigBee protocol vendors and supports more devices from various IoT manufacturers. It also provides diverse device-specific description files for underlying hardware and peripheral interrupt configurations. Another problem we need to consider is test generation. Compared to existing protocol fuzzers, a good protocol fuzzer should generate highly structured test input and have good fuzzing performance. Thus, we design our framework based on grammar-based fuzzing that constructs test inputs from ZigBee protocol specification. We also utilize the coverage feedback to retain the interesting test inputs for further fuzzing. Moreover, the simulator of IIR does not provide a network interface to transmit test inputs. So we develop a proxy server to bridge the communication between the fuzzing engine and the simulator. The workflow of Z-Fuzzer is shown as this picture. We feed the source code of ZigBee protocol implementation and the message format script as the input to Z-Fuzzer. The format script represents the message format defined in the ZigBee protocol specification. Here is an example about how we represent CCL frame with block-based representation in the script. Before starting the fuzzing process, the offline parser generates a control flow graph file of the source code, which is used for code coverage calculation with coverage report. The test case generator generates test cases based on the format script. Then the mutation engine selects a test case and mutates it. The mutated test case is saved by the proxy server for simulator to read. We also develop an interrupt handler in the stack driver to simulate the UART interrupt by reading the incoming messages from a local file. If you are interested, you can check details in our paper. After execution, we calculate the code coverage to evaluate a test input. If it exercises new code, then we save it as a favored test input and prioritize it in the further fuzzing. We evaluate Z-Fuzzer through multiple experiments. The experiments are designed to answer these two research questions. Can Z-Fuzzer detect more vulnerabilities and achieves a higher code coverage rate? We compare Z-Fuzzer with two state-of-the-art protocol fuzzers, Bufuzz and Puche. Bufuzz is the successor of industry standard protocol fuzzer called 30, and Puche is a model-based commercial fuzzer. Both of them have been widely used in existing research papers. The ZigBee protocol implementation and test is Z-Stack, which is developed by Texas Instruments and widely deployed in the most ZigBee-compliant platforms. For vulnerability detection, we perform our experiments on both simulation environment and the real IoT devices. Our results show that Z-Fuzzer detects more unique vulnerabilities with fewer test cases than Bufuzz and Puche. We have discovered 6 vulnerabilities, and 3 of them have been assigned CVE-IDs with high severity scores ranging from 7.5 to 8.2. We also observed that for the same vulnerability, Z-Fuzzer generates more different vulnerable test cases. We can also detect more vulnerabilities by exercising fewer lines of source code. In terms of code coverage, our results show that Z-Fuzzer is more effective than Bufuzz and Puche. Z-Fuzzer can generate 6 times more unique test cases than the other 2 fuzzers. It can achieve higher line coverage in 78% and edge coverage in 82%. In conclusion, we developed Z-Fuzzer that provides a device-agnostic fuzzing platform for ZigBee protocol implementation. We also improve the test generation process of the grammar-based fuzzing by leveraging code coverage information as feedback to generate higher quality test cases. And we discovered 6 unknown vulnerabilities in Z-Stack. 3 of them have been assigned CVE-IDs with high severity ratings. In our future work, we plan to integrate our execution engine with other state-of-the-art fuzzers and extend other embedded fuzzers with our test case generation engine to fuzz ZigBee protocol. We have released our source code at this GitHub link. Welcome to check the details. Thank you for attending.
Thanks a lot for your presentation. There are no questions so far in our chat, so we will directly move on with the next paper, which is recurring verification of interaction authenticity with Bluetooth network. So basically, they have created a new authentication method for Bluetooth devices, and they worked on a very large data set. I think it was over 200 communication traces from 20 devices. And as far as understood it, this is supposed to be open source software as well, but the authors later on can comment more about it. Travis Peters will be here for the Q&A session, who received his PhD from Dartmouth College and is now an assistant professor at the Montana State University. and he is focused on innovative security solutions for critical problems. So I would now like to give the speakers the stage, and see you later on for the Q&A session. When you have questions, just ask them directly in the channel.
Hi everyone, my name is Travis Peters, and today I'll be presenting our work on recurring verification of interaction authenticity within Bluetooth networks. I would like to begin by setting the stage. The context of our work tends to take place in Bluetooth-based wireless personal area networks. At the center of these networks are humans and their primary interface devices. These can be things like smartphones, tablets, or even these smart home hubs that we know and love today, like those made by Google or Amazon or Facebook or Apple, whoever your favorite manufacturer of those devices are. Around those devices are peripheral devices, and today you can find lots of smart connected devices like smart locks, smart blood pressure monitors, fitness trackers, traditional I/O devices like keyboards and mice. All sorts of things exist today. And there are a lot of great applications of these technologies, but they also pose a lot of risks to end users. It seems like every other day there's new news about some big security issue in consumer devices. So it's reasonable for end users to want to ask questions like, have I been compromised? Does this affect me in some way? Unfortunately, the questions themselves are difficult to answer, and a lot of the best practices and solutions available to everyday people, they're just inconsistent with how we use these technologies, right? There are things like leave Bluetooth off or don't even use it at all. These aren't things that work in an increasingly connected world. Now, to be fair, there are actually quite a few challenges that make this problem difficult to address. The most concerning challenges to us have been specific to Bluetooth and how Bluetooth is designed to operate. For example, when Bluetooth devices first connect, they often pair. And when they pair, they do this operation once and then they trust one another indefinitely. Our work is designed to introduce a recurring verification of device interactions in order to ensure that they are consistent with some expectation. Namely, we evaluate ongoing network communications, extract features, and compare them to learned models that represent authentic behavior or authentic interactions. And then we use this to conduct verification. That verification can then be used to determine whether two devices should continue to communicate or not. We envision inserting our monitor into the hub device situated between the applications that run on the hub device and the external peripheral devices. In our model, raw Bluetooth data that enters and exits the hub device is fed into a parser and segmenter. It extracts features, and it is ultimately used to conduct verification by comparing that traffic to previously learned or retrieved verification models. Now, one important part of this work is how to reliably capture Bluetooth traffic. Most people think that you have to use a sniffer and capture traffic over the air between devices. For a number of reasons, this is really challenging and unreliable. We can, however, reliably capture within the hub device by monitoring traffic over the host controller interface, or the HCI. This is basically the interface between the hardware and software for Bluetooth. With the ability to reliably capture Bluetooth data, the next question becomes, how do we model network traffic? For this, we draw on past work that has done deep packet inspection and used n-grams to model aspects of packet headers and payloads. Now, a single model trying to characterize all packets has been shown to lead to ineffective monolithic models. Thus, we need to construct a variety of models that separate traffic into different groups where similar types of traffic can be associated and compared. This approach does pose some issues in the context of Bluetooth, because Bluetooth doesn't support all of these notions. For instance, some of the conventional notions like ports are not directly applicable in Bluetooth. We did observe, however, that model separation based on ports is effectively meant to separate models based on the underlying protocol and the semantics of the interactions within the context of a specific protocol. Therefore, to capture specific semantics of the underlying protocols in Bluetooth, we introduced our approach to model separation, which is based on hierarchical segmentation on the various Bluetooth protocol layers. This allows us to target specific Bluetooth protocols and the underlying semantics in Bluetooth communications and isolate device-specific characteristics. With an understanding of the methods that we've used and the design of our system, I'd now like to turn our attention to the tools that we've built and the data set that we collected as part of this work. First, we'll focus on the data set and the tools that are used to actually parse and segment traffic and extract features. In order to evaluate our work, we collected a new Bluetooth data set. The data set consists of over 300 Bluetooth HCI traces, which were collected from more than 20 devices communicating with their corresponding companion applications, which run on smartphones. And the devices were intentionally selected from two categories: smart home devices and smart health devices. Each of our Bluetooth HCI traces are actually captured in a separate file, which was originally collected on an Android smartphone. These files were moved off of the smartphone onto a laptop, run through our tools, and used to extract the features that we're interested in on a per packet basis for offline analysis. A critical part of this was actually the ability to access the raw bytes within each packet and segment them based on their different protocols. This enabled us to actually build n-grams that were protocol specific based on our hierarchical segmentation, which we described briefly earlier. In the last part of the talk, I'd like to discuss some of our experimental results. The primary thrust of our experiments is to show that our approach can produce models that are capable of differentiating between sufficiently dissimilar devices, which is necessary to conduct verification. To this end, we evaluated our system in terms of its ability to perform verification at different granularities, or really exploring different notions of dissimilarity between devices and their identities. These could be things like their functional type mixed with information about their manufacturer, or the fact that they are, in fact, unique devices. Since there are more than two classes for each of the granularities that we considered, we followed a one versus all relabeling strategy to decompose the problem into a binary classification task. Namely, we repeatedly fixed a single class to be the target class and combined all of the other classes into a single other class. We then evaluated the verification results produced by VIA using a stratified tenfold cross-validation. Throughout this work, we used different binary classifiers to conduct verification, and while in our complete work we explored various classifiers, in the paper we only actually presented results for the random forest classifier, which was among the top performing classifiers. One question that we examined in this work is, are functionally different devices distinct from one another according to how our models can represent them? For example, is a blood pressure monitor definitely recognized as being a different device than a heart rate monitor or a smart lock? We observed that our models are in fact capable of creating clear separation between these different types of devices, and that our system could achieve an F1 score of 0.9 or better in all of the cases shown here. Another direction that we explored was our system's ability to distinguish among distinct instances of devices. The results here revealed that VIA does in fact struggle to distinguish between highly similar devices. So for example, in our data set, we have two instances of otherwise identical environment sensor devices. They run the same hardware, software. These are identical devices, but they are in fact distinct instances of these devices. We have another example of this issue with our Polar H7 heart rate monitors, which also show that the models were not very coherent in terms of distinguishing between these devices. If you were to exclude these examples, however, we can actually see that our system performed very well. I mean, there was an F1 score of 0.86 or better in all of the other remaining cases. And While this points to a potential limitation of VIA's ability to distinguish between distinct devices, we argue that this result does not undermine the value of VIA, because our objective really is to verify the authenticity of interactions. And so confusions between models that exist for an application and devices that appear to function and communicate in nearly identical ways doesn't pose an immediately obvious threat to the devices or the applications. To recap, we've presented a new recurring verification scheme for Bluetooth. We've chosen to focus on the challenges around designing and evaluating models which are necessary for the actual verification procedure. We've also collected and shared a new dataset that has more than 300 Bluetooth HCI traces, as well as enhanced tools that will hopefully aid in future Bluetooth-related research. We have also presented details about the experimental implementation and evaluation of our system, which shows promising results when conducting verification. For those that are interested, we invite you to check out more details in our paper, but for now, I'll leave it there. Thank you very much.
Thanks a lot for your presentation. We will focus on the questions in our question and answer session at the end of the session. And now we will come to our third presentation, Happy Man in the Middle, Fun and Toys in Every Bluetooth Device. This will be presented by Jiska Claassen, who is a security researcher at TU Darmstadt. And she has been around here for a while, breaking all kinds of things in Bluetooth firmware. I would now like to give the stage to Jiska Claassen, and when you have questions, just post them in the channel on Slack, and we will then come together for a question and answer session at the end of the session.
Hi everyone, I'm Jiska, and this is my presentation about a Bluetooth user interface issue affecting all major operating systems, which makes ongoing machine-in-the-middle attacks very stealthy. Alright, let's take a closer look at this happy mitten box contents. Secure Bluetooth pairing modes, called passkey entry and numeric comparison, require the user to enter or compare a number. This prevents active machine-in-the-middle attacks. Think of this like a TLS handshake. However, Bluetooth works offline and without any trusted certificate list, so user interaction is required to guarantee a root of trust. Recently, multiple midterm attacks on secure Bluetooth pairing modes were published. This demonstrates that Bluetooth security is flawed. Yet, many devices do not even use secure pairing modes. Most headsets and IoT devices do not have a display or keyboard to compare or enter a number. In this case, the so-called just works mode, which skips the steps and enables active machine-in-the-middle attacks by default. However, this is only possible during the initial pairing, which enables keys, meaning that Bluetooth uses trust on first use. So here you can see a pairing with two keys, and in a setup with the just works mode, and well, here you can see that if one exploits this, then you would get separate keys. So the machine-in-the-middle attacker actually replaces messages towards both ends in the pairing process, and this is not noticeable by the device under attack. And there was a lot of hype around secured pairing modes, but I never cared a lot because, well, the just works mode is just there, and then for many devices attacks are possible anyway. And then second, an attacker must not only break the initial pairing, but they must also be present in future connections. And if you look into a mobile setup, this is very challenging because the device under attack is moving, and if the attacker just fails once, messages and keys become inconsistent, and this could be detected by the device under attack. So the expectation is that if we have, or if we know that we have a possible machine-in-the-middle attack in a browser, for example, then we would see a warning like this. So if something goes wrong with certificates, or in our case, trusted keys in a Bluetooth pairing, the user should see a warning. But the Bluetooth specification really overcomplicates security warning options. So in most cases, so the blue cases here, the user is required to see a notification of a security failure, but there are also various other options where it's kind of optional to warn the user or start a new pairing depending on the key type, if it was bonded or authenticated and so on. So it's really confusing what to do here. So the first requirement to even warn the user at all would be that the Bluetooth chips on both ends of a connection realize that there was an authentication failure. And then they should inform the operating system and ask the user, like iOS or Android. So the Bluetooth specification is a bit misleading here. There's this HCI layer between the chip and the operating system, for example, Android, but it's optional. So in an IoT device, it would just be one chip without this HCI part. And this is something that they do for having lightweight IoT implementations. And for such implementations, LMP would not send any HCI message, but directly send an LMP disconnect to another chip with the error code of an authentication failure. But as soon as you have HCI, the chip is then informing the operating system on top instead. And then the operating system must somehow inform the user and is involved into this process. And this can introduce further errors. So on the way back, in the case of Android, the connection is still terminated, but Android just says, yeah, this is user terminated. And then the error code that the connection is just ended because of the user interaction is also forwarded to the remote chip. So the remote chip in some scenarios with Android just thinks, oh yeah, it was just a regularly terminated connection and not a security failure. But in most cases, initiator and responder would see an authentication failure, and then ideally the operating system would warn the user with some easy to understand pop-out as the one that I just have shown before. So then there's something unexpected. So none of the devices that we tested would warn the user in such a way. And even worse, Google Android would just delete the pairing without displaying any message. So this is even the case for permanent pairings with numeric comparison. So pairings that were bonded and authenticated, and that allows reinstalling keys for machine-in-the-middle attacker under certain scenarios, or it makes it easier to trick the user into reinstalling keys. And then all the other devices would not show a warning, and once the attacker is successfully using the old key before, etc., they would just continue with this wrong key or with the key that in between was not working without showing any warning, etc. So this was not what I expected. And here's the overall list, and you can see that the issue is independent from the Bluetooth version, so it's just there in all operating systems because it's in the user interface. And except from Google Android, an authentication failure looks just exactly the same as a regular connection failure. In this video, you can see an iPhone Bluetooth packet log on the left-hand side. The left smartphone is an iPhone 8, the right smartphone is a Google Pixel 5. And in the iPhone, we install a script that creates a controlled authentication failure similar to a machine-in-the-middle attacker. To do so, the script temporarily changes the connection's link key, and the output of the script is shown in the bottom. Once the Pixel user clicks on the paired iPhone to initiate a connection, the iPhone immediately disappears from the paired device list without a warning, and this is very confusing and makes it easier for attackers to trick users into reinitiating an insecure pairing in their presence. The iPhone's packet log contains an authentication failure because the key was changed on this end. So note that depending on who initiated the connection and where the key is changed, one would also see the case where you just see a remote user terminated connection instead of the authentication failure. And here in this video, you can see two iPhones. Upon an authentication failure, the device will only show that the connection was unsuccessful, which is the same error message as if the other iPhone was turned off or out of range. Once the iPhone switches back to the old key, the connection works again. As you can see, an ongoing machine-in-the-middle attack really looks just the same as a connection failure to the user. This machine-in-the-middle issue is anchored in the user interface, which should be hardened. It is not yet another Bluetooth machine-in-the-middle attack. So Apple and Google classified this as a security enhancement and will address it in a future release. But keep in mind that machine-in-the-middle attacks are always possible in the just works mode. And then surprisingly, Microsoft just closed the ticket and claimed that users had no way to interact upon a Bluetooth security warning, and because of this, they will not add any warning dialogues. Then I did not follow the intended process for opening a security issue in GNOME apparently, and because of this it has been a bit messy, but they are currently looking into this and will also address the issue very soon. The process with Xiaomi had been really weird, so they had additional questions, but the questions did not really address what I explained to them, even though I explained it multiple times, and then at some point the issue was just closed because of inactivity. And also interesting is that I mailed Bose twice, but I didn't get any automated response to my mails and also no other response from anyone, so I'm not sure if that mail address is working, despite it's even listed as a security contact, including a PGP key. You can very easily try to change keys on your own. On Linux, you can just change the configuration file, and on iOS and Android, I created more generic scripts which can replace contents of HCI messages during runtime. These scripts might also be helpful if you want to test anything else within a Bluetooth stack here. There will also be an internal Blue tutorial later during this WiSec, so in case you want more details or have questions about internal Blue setups, you can go there.
Thanks a lot. So we already have a few questions in the channel, but I would now like to give the stage to our last presentation first. So our last presentation is titled "No Need to Ask the Android, Bluetooth Low Energy Scanning Without the Location Permission." For this presentation, we will also have Mathy here, who's currently an associate professor of the University of Lyon. His research focuses on security and privacy issues in wireless networks and mobile systems, and he will later on be here to answer a question in the question and answer session. And one of the things that was highly valued by our reviewers was that this paper has a very high impact, and there are actually some CVE numbers attached to it. So now, please give the stage to our last presentation, and then we will see each other again for our Q&A session with all the authors of this session.
Hello, my name is Mathy, and today I'm going to present a joint work with Vincent Toubiana. Our work is about Android and its Bluetooth low energy features. And in our talk, we're going to see how we can bypass some of the restrictions that are applying to Bluetooth low energy scanning. First, a couple of words about Bluetooth low energy. So as you know, this is a variant of Bluetooth that has been designed to fit the needs of devices with low energy capabilities. It is a technology that is implemented in many devices, such as smartphones, tablets, and laptops, but also many connected devices, such as TV, earphones, smartwatch, and more. On Android, an application can use the Bluetooth energy features of the device. It can do so by using some method of a dedicated API. There are two main methods here. The start scan method that is used to start the scanning process, and the on scan result method that is used as a callback to get to pass the results to the application. In addition, it's also possible to specify some characteristic of the setting. So you can use, for instance, default scanning, in which all the records are passed to the application on the fly. But you can use batch scanning if you want to save energy, so the scans will be returned in batch at a regular interval to the application. So in which case you don't use the on-scan result callback method, but you will use the dedicated on-batch scan result. Furthermore, it's also possible to apply some filters to the scanning. So in which case only records matching a specific criterion will be returned to the app. For instance, you can select the device name, the type of address or the prefix of the address, company ID or UUID. But wireless scanning can be a privacy threat. This is something that we have demonstrated a while ago with a publication here at WiSec, where we showed that malicious applications can abuse a Wi-Fi scan. We show that the result of those Wi-Fi scans can be used to derive the location, and so a malicious application can get the location of the device without asking for the location permission. Following that, the FTC started an investigation based on our results and conducted an investigation which resulted in a company called InMobi to be fined for almost $1 million. Also, Android changed its permission system. So to protect users against the threats, since version 8.0 of Android, the location permission are required to perform Bluetooth and Wi-Fi scans. How are they applied in practice for Bluetooth Low Energy? So you can start a scan if you have the location setting that is enabled. So this location setting is the one that makes this small icon appear on your screen. Or if your scan is filtered. So Android considers that filter scans are less sensitive with regard to location. And those constraints are enforced inside a method called handle start scan, which checks if those two conditions are met. To get scan results, the app must have the location permission. This is something that is clearly documented in the Android website. And the location setting must be enabled. So both of those restrictions are again implemented in a method called asScanResultPermission, which check that both those conditions are met. And this asScanResultPermission is used inside the onScanResult, so the callback method used to pass the result to the application. And if this verification is not successful, result will not be returned to the application. But this same verification is not done on the on-batch scan results, the callback method used for batch scanning. So this means that batch scans will be returned to the application even if the location permission has not been granted to the app and even if the location setting has been disabled. So as we saw, there are some gaps in the verification of those restrictions. Especially between on-scan result and on-batch scan. And we thought that maybe it would be possible to find some combination that will allow to get some scanning without requesting some of those conditions. First things we can do is to do batch scannings, in which case we start the scan, which will only require the location to be enabled, and then the result will be retrieved through on-batch scan result, which does not require nor the location permission nor the location to be enabled. So in the end we get scanning without the location permission, and location is only needs to be enabled at startup. We can add on top of that the filter. So we still perform batch scanning, but on top of that we filter the result. In which case the start scan does not need to have the location permission nor the location to be enabled, and still for the result we don't have any restriction. So we have scanning without any restriction, but the results are filtered, which may be a problem, but we can try to design filters that are very loose and that will include a large number of records, for instance by matching popular UUIDs or OUI. But even more, we can design a filter that will include everything. So we found out that there is a way to create a pass-all filter. So there is a bug in Android which allows a filter to be created and that will keep all the records. And this filter can be created, for instance, with this method. If you pass the specific parameter null here instead of pointers to buffer, you will create a pass-all filter. So this means that using a batch scans that is filtered with this bogus filter, you will be able to get all the results without the location permission and with the location setting that is disabled. So you are bypassing everything. And those issues had a serious impact on Android. So all the versions of Android between 6 and 11 are affected. Hopefully, there is a patch that is already available. So Android assigned a CV to this issue and released a patch in the security patch of last February. Regarding the filter issue, it's still under investigation by Google, but they consider that it's not as critical as the other one, so no CV will be assigned. These privacy vulnerabilities will be fixed if you apply the patch, but as you know, on Android, many devices are not receiving updates. So a good number of devices will remain vulnerable, and especially the older devices. So let's move to the conclusion. So what are the causes of those issues? The first one is inconsistencies between the implementation of the restriction, as we saw between the on-scan result and an on-batch scan result, which are performing the same task, but in which the same restriction were not implemented. Also, there is a bug in the filter configuration, and which allow application to get all the results. And in addition, Android considered that filter scans are less sensitive than non-filtered ones. Are those issues exploited in the wild? We don't know. We haven't checked all the application. We only done a superficial verification, but a proper investigation is required to make sure that no application is using that. How to avoid this kind of problem in the future? So we saw that there were a lot of problems coming from the way the code was written. So better documentation of the code and the way privacy features are included will ensure that in the future developer will not make the same mistake. Also, we can think of methods such as formal verification to ensure that those restrictions that we saw before are properly implemented and that there is no gap inside this implementation. Thank you for your attention, and if you are interested by those vulnerabilities, you can check our GitHub, where we have a proof of concept that you can test on your device to see if the vulnerability is applying to your device. And if you want to get in touch, here are our email. Thank you for your attention.
Thanks a lot for your presentation. And now we will come to the Q&A session. So I would like to ask every speaker that presented something here to come online now in Zoom and also activate the camera. And we have actually a few things that could be interesting. So the speaker of the first presentation was Meng, who's currently a PhD candidate at the University of Texas at Arlington, who's doing research focused on software testing and IoT security. And one question that could be quite interesting for the audience is when you now get excited about ZigBee research, how does the landscape look like? So how many different stacks are there? How many different hardware vendors are there? Do people usually modify the stacks, or are those stacks usually open source, or are they usually available as binary only or something like that? So how's the landscape there?
Yes, as we know, right now there are several protocol vendors already listed in the ZigBee Alliance website. The most famous like Texas Instruments and also NXP and Silicon Vibe. They also have some ZigBee protocol implementation, but not all of them are open source right now. So for ZigBee, you can directly find their implementation called the Z-Stack on their website. And also NXP, you can get their source code when you purchase their devices. It's separate SDK with the device website. And also for the stack itself, it's depending on the manufacturer's application. Some may modify the stack itself. This also when we discussed with TI, they say they suggest that if you find some problems, feel free to add your own code in our stack. So it's depending on the manufacturer's application and their requirements. If they need to modify the stack code, I think the protocol vendor are welcome to let them to add something. And for the I think that's for these questions. Yeah, there are some different stacks, but currently we just test the protocol stack from TI, and we plan to test more protocol stacks in our future work.
Excellent. So that looks like there is still some kind of unexplored playground out there for really good fuzzers that fuzz the ZigBee protocol. Thanks a lot.
Thank you.
So our next paper, that was recurring verification of interaction authenticity with Bluetooth networks. And there was a very active discussion on the channel regarding this paper. So one of the questions that was asked here was, using your approach, is it possible to differentiate between rare interactions, for example, a type of advertisement data packet unseen during training, and malicious interactions? Can you please say something about this? Travis, are you online?
Yep. Can you hear me okay?
Yes, we can.
Okay, yes. I provided a brief response in Slack if people want to revisit this later, but in short, this is actually a really interesting direction that we're hoping to explore more of in the future. Basically, I think this question doesn't just get at advertisement data because we were looking at health data and things like that. We were actually interested in what if someone were wearing a device that, for example, a heart rate monitor, and then they undergo some extreme health event like a cardiac arrest or something. What would their heart rate monitor would show, and would that kind of trigger an anomaly in our system? And the answer right now is probably yes. We haven't gotten to explore it too much, but in the future, we're hoping to look at kind of two different directions. One of them is just kind of looking at the sensitivity of the classification and kind of the thresholds that are set for when anomalies are detected. And then the other would be actually looking at the n-grams, which are pretty fundamental in the anomaly detection models that we have right now. And if you can actually isolate portions of that are associated with fields within the communications that would be prone to high variability, that might kind of trigger these false detections in terms of security events, then you might be able to kind of downweight or at least lessen the impact of those in the verification.
Yeah, thanks a lot. And then we also had a second question on the channel. That was, authentication during the reconnection process of Bluetooth Low Energy is optional. And if I understood the motivation of this work correctly, this is why recurring verification is proposed. If the re-authentication becomes mandatory during the reconnection process, do we still need recurring verification?
Yeah, and again, there's a little bit of back and forth on Slack that folks, I invite you to check out. The short answer, I think, is yes. I think what is being discussed here is really just this idea of making something mandatory that's optional, but it would still kind of be a traditional authentication that would be based on long-term keys or something like that, for example. In our case, we're proposing what we would like people to think about as a second factor, which would be an authentication that's actually done, a second form of authentication that's actually done based on a network profile, and that would be used kind of in conjunction with some initial authentication mechanism. So yes.
Thanks a lot. By the way, the data that you're using, where can we find that? Can you maybe put the URL in the channel or something like that?
Yeah, well, there's a short answer and a long answer to that. The short answer is I believe ACM and WiSec in particular host a collection of VMs that are kind of totally packaged up with the necessary source code and tools. And so that should be available anytime, I imagine. I guess I'm not sure when that will be available, but then you can download a VM and everything's there for you. There was a little bit of a snag in releasing things through our dataset channel. We're using the Crawdad project, and I need to work out a few things there, but that's a big repository for wireless data sets. And so I don't know if there's a way after the conference to share links to that, but there will be links to those things in particular in the paper. There's actually links to the source code that are available in kind of a couple of different spots, and then a kind of a link that exists but is currently kind of empty, but the data set will be uploaded to that link. So that's there and available in the paper. For people that want stuff sooner, I would encourage you to check out the VM that's being hosted on WiSec's servers.
Thanks. By the way, last thing was, do you have an idea or measurements on how the classifier performance might change over time?
Yes, another good question. Thank you. Unfortunately, because of space constraints in the paper, I had to eliminate a piece of discussion about this, but we've explored a few mechanisms, but because of when the data set was done, or was collected, and when the analysis was done, we actually weren't able to explore this particular scenario where you're looking at how a device and its interactions change after one or more updates. And so in Bluetooth, there are kind of some specified mechanisms, like for a Bluetooth server in BLE to announce basically that services have changed. And in our current thinking, we're hoping that that could trigger kind of a retraining or a fresh download of a network profile that would be used for the verification. But we don't have any current measurements on this right now.
Okay, thanks a lot. Yeah, there was really a lot of interest in your paper. But now I would like to give the word to Jiska Claassen from Technische Universität Darmstadt. And there is also a question I have for you. Is there any good product that interacts with the user in the way you want it to be?
I mean, it really depends on the point of view on that. I think for browsers, we already have that. So there are browser warnings and everything. So once there goes something wrong with encryption, I would say browsers are at the point where it's good. And also one thing that recently happened to me is my neighbor just went to me and asked me like, hey, my iPhone shows me a warning that my Wi-Fi is insecure. It just uses WPA and not WPA2. What does it mean? So I think there is really good interaction in that way that people are warned when there's something wrong. And I mean, in that case, it was just me helping my neighbor to secure her Wi-Fi. But yeah, so I think there are good ways.
Great. So then I would like to go to our last paper. There was actually also a question on the channel for Mathy. I hope you're online. How was the pass-all filter vulnerability determined?
Yeah, I saw those questions. So in fact, there is no. It was just luck. So we've identified when looking at the code that filtered scan were handled differently, and that we can augment the attack by using filters. And when we tested the attack, I just used default parameters, null, and I found that there was this strange behavior. So it was not very interesting the way we found it. However, something that I've not presented here, but it's inside the paper, is why is this bug around? So we've digged a bit inside the code, and we discovered that it's rather interesting. So the filters can be offloaded to the Bluetooth controller. So in this case, the controller will perform the filtering itself and will only return the matching scan results to the operating system. And to configure the Bluetooth controller, the operating system needs to send some HCI command to the controller to configure the filter. And when the filtering is offloaded to the controller, the operating system will not perform, will not apply the filter once more when it receives them from the controller. But for some unknown reason, when we create the filter with null parameters, no HCI comment is sent to the controller. So the controller is not configured, but the operating system believes that the controller will apply filters, so it will not apply filters again. So on one side, you have one device that does not perform filtering, the other one believes that it's doing filtering, and in the end, everything is passing through, and you don't have the same restriction that are applying because the OS believe that the filtering is applied.
Well, that sounds like a typical problems that you get when you interact between different layers of software. So apparently the programmers of the API didn't really know how those filters were implemented in the lower layers. And that's unfortunately something that you see quite often when you look at computer security. Thanks a lot.
Right.
I think this concludes our session. We now have a 20 to 25 minutes break. And after that, we will continue with session 3, Wi-Fi and vehicular network security. And when you would like to see me again, then you can see me again as the host in our poster and demo session on Wednesday. And until then, you can also check out the trailers we have for our poster and demo session. And of course, the trailers for our regular papers here, which are linked in the program as well. Always with the small purple, blue YouTube-like icon next to the actual paper title. Thanks a lot. Thanks to all our speakers. Those were really great presentations. And when you still have questions, you can ask them on Slack, either ask them here in the channel or contact the speakers privately. I linked all their accounts during the session in the channel. Have a good time, have a lot of joy with WiSec, and see you again soon.
Okay, welcome back, everybody. Welcome in this third session and last session of the WiSec conference of today about Wi-Fi and vehicular network security. Before we dive into the technical content, just let me remind you of the practicalities. So we'll first have the presentations one after the other, and then after these presentations, we have a dedicated Q&A session. So if you have questions regarding one of the papers, you can ask them on our dedicated channel for this session. So session 3 on Slack, you can ask your question there, and please also indicate for which paper you're asking a question. And then I will go over them one by one. If you also see a particular question that you say, oh, this is one that I also want to ask, this is a very interesting one, you can always give it a thumbs up, and then I will start with these ones first. I think that is probably most of the practicalities. So, okay, let's start with the first paper. The title of the first paper is Let Numbers Tell the Tale, Measuring Security Trends in Wi-Fi Networks and Best Practices. And this paper will give us some insights on how Wi-Fi security is deployed in the real world. And this presentation will be given by Domien Schepers. Domien has a master's in computer science at KU Leuven, so the university where I'm working, and is now a PhD student in Northeastern University. So I'll hand over the virtual floor to Domien.
Hello, my name is Domien, and this is Let Numbers Tell the Tale, Measuring Security Trends in Wi-Fi Networks and Best Practices. This work was done in collaboration with Hancke and Gerhard from Northeastern University and Mathy Vanhoef from New York University, Abu Dhabi. The Wi-Fi standards, formerly known as IEEE 802.11, are an ever-evolving set of standards for wireless networks. They have continuous improvements for better performance, throughput, security, and more. For example, recently they standardized Wi-Fi 6 and Wi-Fi Protected Access 3. These offer improved security, for example, an improved key exchange named Simultaneous Authentication of Equals, and made it mandatory for networks to support protected management frames. In recent years, we have seen a push for improved security. For example, vendors display warnings for insecure configurations, the Wi-Fi Alliance presented visuals for each Wi-Fi generation, we have seen the official deprecation of insecure protocols such as WPA-TKIP, and the countless efforts by researchers and enthusiasts. However, we find that deprecated protocols remain supported in practice. For example, over 30% of networks supported WPA-TKIP in October 2020. So we wondered, what is the effect of this recent push for improved security? What are the security trends we observe today? And what is the state of today's overall security landscape? To answer these questions, we analyze public datasets such as Crawdad, Wiggle, and radio cells. However, they have their limitations, for example, incomplete data or outdated. Therefore, researchers are required to perform their own survey, and these come with their own challenges. In this paper, we perform our own survey of over 250,000 Wi-Fi networks. We measure security trends for modern protocols and standards, and highlight the importance of a survey's region and frequency band. We recommend best practices to perform and present the Wi-Fi survey, and publish all tools and datasets to enable and stimulate further research by the community. We will analyze a variety of datasets, such as public datasets. These often crowdsource their data, often through Android applications. For example, Wiggle has the most extensive collection of over 750 million Wi-Fi networks. Radio Cells offers data on Wi-Fi and cellular networks, however, is discontinued. And Crawdad is a community research archiving various wireless datasets. They have their limitations though. For example, the raw and full beacon frames may not be available. This is a result of, for example, the Android API, which restricts this kind of information to end users. As a result, there are missing information fields that are needed to, for example, inspect support for protected management frames. Therefore, we performed our own Wi-Fi survey between October 2019 and May 2021 across 4 countries and 3 continents, and with a total of 250,000 Wi-Fi networks. We have passively captured beacon and probe response frames on both frequency bands and defined the uniqueness of a network using its MAC address. This increases the weight of large networks and reveals how many devices support a certain feature, which is useful to measure an attack's impact. From related work, we often see missing information on which frequency bands the survey took place, and therefore it is a best practice to always address the survey methodology. From related work, we've also learned that certain frames can leak privacy-sensitive information, and therefore it is a best practice to preserve the privacy in published datasets. We do so by releasing only a single frame per network to limit the leakage of potential sensor data, remove the client ID part of a MAC address, and map SSIDs to incremental pseudonyms. From our surveying efforts, we measure security trends in which we identify key observations and insights. For example, in any wireless survey, the methodology, such as the region, directly impacts the results, and Wi-Fi networks are no exception. For example, we find that support for WPA-TKIP ranges from 20% in Boston to over 45% in Hasselt. Similarly, Radio Cells reports large differences even for neighboring countries. For example, Radio Cells finds 21% of WPA-TKIP support in Italy and 48% in France. These differences can even be seen within a single city. In our Boston neighborhoods, the results varied between 30 and 37%. And therefore, it is a best practice to try to survey a sufficient number of distinct regions. Similarly, we can see this with the frequency bands. Since not all protocols operate on each frequency band, there are some notable differences. For example, Wi-Fi 5 defines physical layer improvements for operations within the 5 GHz spectrum. So if we split our 2020 datasets on a 2.4 and 5 GHz spectrum, we see large differences for Wi-Fi 5. Therefore, it is important to not only measure the adoption rates on the appropriate frequency bands, but also present the resulting statistics for each of them. Furthermore, we inspected the security differences of 2.4 and 5 GHz networks on the same hardware device. To do so, we matched the first 5 bytes of the MAC address and 2 bytes of the SSID within a restricted time window to identify an access point broadcasting a network on both the 2.4 and 5 GHz spectrum. We found that most insecure 2.4 GHz networks do not have a counterpart on the 5 GHz, and therefore we conjecture these are older access points with insecure capabilities. Another major factor which distinguishes a region are the internet service providers. And to measure their impact, we performed a case study in Belgium where we tracked the default security configurations over 3 years' time. For the longest time, support for example, WPA-TKIP did not change until the end of 2020, when ISP Telenet updated its configuration. They removed support for the deprecated protocol, and overall in Belgium, its support dropped by more than 37%. This means that ISPs have an overwhelming impact on the overall state of security, and highlights the importance of phasing out these protocols. We see the similar thing happen with Wi-Fi Protected Access 3. Even though they were released in 2018, its support in practice remains very low. Today, we did not find any Wi-Fi network which supports WPA3 only, and merely 0.06% was in transition mode, which means that the network supports the mandated protocols, but does not actually mandate its usage. So, despite all the efforts, the adoption of these modern standards remains low. Finally, we find an increasing prevalence of hidden networks. These networks do not broadcast their network name. They are not recommended for typical home users because it, in fact, compromises client privacy because of broadcasted probe requests. However, since we find their presence increasing, we had a closer look to them. We find that they have quite a distinctive security configuration. For example, only 2% supports Wi-Fi protected setup. This suggests that they are not meant for your typical home users. And instead, we find them to be part of mesh networks and smart city infrastructure. They hide their presence, which prevents them from being displayed in user interfaces. It is interesting future work to study and determine their exact purpose. We publish all our anonymous data sets of over 250,000 Wi-Fi networks on our repository. We present detailed statistics per date, region, and frequency band as well. We provide all the tools to extract statistics from the network captures and the tools to anonymize network captures. In conclusion, we performed an extensive survey of over 250,000 Wi-Fi networks across 3 continents and measured the security trends within them. We've seen the slow adoption rates and everlasting support for deprecated protocols, and an increase for mesh networks. We've highlighted the importance of the region and the frequency bands, and stressed even more the importance of ISPs to drive the adoption of secure protocols. We've recommended best practices to perform and present a survey, and published all our tools and datasets online. Thank you. My name was Domin, and this was Measuring Security Trends in Wi-Fi Networks and Best Practices.
Thank you. So we immediately go to the second presentation on Wi-Fi security. By the way, a reminder, if you have questions for Domin, please ask them on Slack, and then we'll come back to them in the Q&A session. So we stay in the Wi-Fi domain, but now we're going to look at the Wi-Fi localization, and more particularly to Wi-Fi FTM. And so the second presentation is Here, There, and Everywhere, Security Analysis of Wi-Fi Fine Time Measurements. And this paper will also be presented by Domin. So we have the same author again. So I don't think he needs a reintroduction again. So we can immediately go now to the second paper.
Hello, my name is Domin, and welcome to Here, There, and Everywhere, Security Analysis of Wi-Fi Fine Timing Measurement. This work was done in collaboration with Mridula Singh from ETH Zurich and Anjan Ranganathan from Northeastern University. Wi-Fi fine timing measurement enables 2 stations to measure the distance between them. It offers meter-level accuracy and is used for purposes such as indoor positioning. It was standardized in the 802.11 MC amendment and incorporated in the 2016 standard. Since then, it was also adopted in Wi-Fi Aware for purposes such as geofencing. It has been supported by vendors such as Intel and Qualcomm and has seen support since Android 9. In this paper, we present the first security analysis of Wi-Fi FTM. We find weaknesses across the logical and physical layer, which result in a variety of distance reduction and enlargement attacks. Some are even independent of any higher layer cryptographic protection. We make recommendations for Wi-Fi FTM, as well as next-generation protocols to increase security, and we release all our tools on GitHub, as well as practical tutorials and an overview of security vulnerabilities and patches. In the protocol, the client makes a measurement request. It includes parameters such as the number of measurements, the bandwidth, and when the responding stations accept this request, it will start to measure the round-trip time. It does so by taking the time of departure of the response frame and measuring the time of arrival of the acknowledgement. This process is repeated a number of times and allows the initiator to measure an average round-trip time. If both stations wish to measure the distance, they have to switch roles and run a new measurement. In our paper, we performed the first security analysis of Wi-Fi FTM. The standard provisions few means to provide security or privacy. For example, there is no authentication or confidentiality. However, this does allow for seamlessness and accessibility. For example, it allows clients to localize themselves in indoor shopping centers without authenticating to access points. Furthermore, there is support for Wi-Fi MAC address randomization, and while this is optional, it is enforced on all the Android smartphones we have tested. As a result, there are trivial distance enlargement and reduction attacks, for example by spoofing or replaying response frames. Consider the protocol. The initiator makes a request, however, does not know who is responding. The adversary can therefore inject spoofed response frames and, for example, replay frames or tweak the timestamp values. If the adversary adds or subtracts time to these timestamps, it proves to be a great way to make relative changes to the client. However, what if we want to forge absolute distance measurements which are independent of the client position? Then it becomes more difficult, because we have to find a way to estimate the difference between T3 and T2, that is, to estimate the processing time at the initiator. We found a way to estimate this value through a benchmarking technique. In this technique, we report a constant round-trip time. When the client receives this round-trip time, it measures a distance, and this allows the responder to measure the average processing time. That is, since we know the round-trip time as well as the measured distance, we can deduce the time spent at the initiator. This proves to be a great way to create spoofed timestamps independent of the true client position. We have made an evaluation against a wide variety of devices supporting FTM, such as Google, Nest, Asus, and CompuLab access points, as well as smartphones such as the Pixel 4 and off-the-shelf Wi-Fi cards by Intel. For the adversary, we do not require any expensive equipment and can use a simple commodity hardware such as a TP-Link Wi-Fi dongle. To evaluate our benchmarking, we run over 1,000 sessions against every configuration. From this, we see, fortunately, that Wi-Fi cards of the same make yield the same results. So the same Pixel 4 smartphone will have very similar results with a little deviation. So this proves to be a great way to spoof the distance. For example, with the Pixel smartphone and the wild access point, we find that we have meter level accuracy when we spoof the distance between, say, 2 and 20 meters. Notably, this adversary has no location restraints. It can be anywhere within range of the protocol, can be stationary or mobile. Until now, we have seen how an adversary can introduce distance reduction and enlargement attacks using the protocol layer. However, more weaknesses exist on the physical layer. Since the standard provisions no physical layer security, it allows for more complex distance enlargement and reduction attacks. Some of these are independent of any higher layer cryptographic protection of, say, the response frames. As a first example, consider unexpected physical layer parameters. We find that an adversary can manipulate the distance by replaying frames with an unexpected configuration, for example, the bandwidth, the modulation, or the guard interval. This results in a replay attack which relies on two shortcomings. First, the lack of verification of the physical layer header, as well as the incorrect management of saved timestamps. Consider the client. It receives a response frame and measures its time of arrival T2. It then sends an acknowledgement and measures the time of departure T3. However, when an adversary modifies physical layer parameters, it effectively changes the overall transmission time. For example, using a short guard interval will reduce the time between symbols and as such have a shorter overall transmission time. This results in a T3 timestamp, which is smaller than before. This can be used to create a replay attack, where the adversary replays a frame with modified physical layer parameters. Since the client does not verify this, the frame is accepted. However, when the responder sends the legitimate frame, the client will discard it because it has already received this frame and doesn't need it anymore. However, it will still transmit the acknowledgement. The responder is not aware that this frame was discarded and therefore reports the T1 and T4 round-trip time of that measurement. So now the client uses an incorrect set of timestamps. That is, it uses T2 and T3 from the adversarial frame, but also uses the round-trip time from the session with the responder. And as such, we can introduce distance reduction or enlargement attacks. We have evaluated this against, for example, the CompLab Wild and Google Nest access point on over 1,000 sessions with the default configuration of 80 MHz, BPSK modulation, and a long guard interval. By default, we have a distance by some 15 meters, but when we change the physical layer parameters, we see that these distances change quite significantly, both reducing and enlarging. Though it is worth to note that we have only changed the physical layer parameters over a single frame, and we can use combinations to increase the granularity. For example, we've done an experiment with a short guard interval, 20 MHz bandwidth and 16 QAM modulation, which resulted in a distance reduction of some 10 meters. So any combination can be used to achieve the desired result. Next, we show how acknowledgements can be overshadowed. An adversary can simply spoof acknowledgements with commodity hardware by assuming the MAC address of the client station. This does require knowledge of the MAC address and becomes only challenging if this is randomized. However, notably, this attack succeeds even when response frames are protected. In our evaluation, we've used the Wild and Nest access point, and we see that we can achieve meter-level accuracy when we simply acknowledge response frames and this evaluation between 2 and 20 meters. From our findings, we can construct a number of countermeasures. These are valuable not only for Wi-Fi FDM, but also for next-generation protocols. First, the clients have to perform physical layer header verification and discard frames with unexpected bandwidth, modulation, guard intervals, and so on. Next, an initiating station can add a random time delay before transmitting an acknowledgement. As a result, benchmarking techniques will be inefficient and therefore cannot be used to introduce distance alterations. Next, any response frame that is detected as a replayed frame should be discarded. Perhaps even the entire session should be discarded as to make sure that no alterations were made. Additionally, stations should enforce a lower and upper bound to the round-trip times, say between -10 and 100 meters, and discard any results which are beyond this. Finally, Wi-Fi MAC address randomization should be enforced. We provide a repository with all our tools to experiment with FDM, such as distance modification, and release tutorials with practical configuration and setups for the protocol, and finally track the adoption rates of FDM, vulnerabilities, security patches, and more. In conclusion, we find that Wi-Fi FDM is fundamentally insecure. It should not be used for security or privacy-sensitive purposes. We presented numerous recommendations to increase the security, which are valuable not only for FDM, but also for next-generation protocols, and identified all identified issues are disclosed to the vendors. Thank you. My name was Domine, and this was Here, There, Everywhere, Security Analysis of Wi-Fi Fine Timing Measurement.
Thank you, Domine. Again, we'll first go to the third presentation and then discuss questions during the dedicated Q&A session. So if you have questions about this task, about this presentation, sorry, don't hesitate to put them on Slack. So now we first go to the third presentation, and the first two presentations in the session were about Wi-Fi security. Now in the last presentation, we go to vehicular network security. So more in detail, we're going to look at a particular type of message which is used in V2X networks, which is called the basic safety message, or BSM. And so we'll see how these BSM messages can be attacked and can create quite serious safety problems and how to mitigate them. The presentation is given by Siddharth Tonke, I hope I pronounced it correctly, from Rochester Institute of Technology. And so Siddharth did his master in computing security at Rochester, and now he's doing going for a PhD at the same institute. So Siddharth, the floor is all yours.
Hello, and welcome to the presentation of our work, in which we propose a novel message sieving technique to mitigate smart gridlock attacks in V2V. I am Sid, and I co-authored this work with my advisor Dr. Hanif Rahabri in the Wireless and IoT Security and Privacy Lab at Rochester Institute of Technology. As more and more vehicles are pouring into roads, dense roads are becoming more prevalent. Roads like the one you can see in this image, where vehicles are in proximity and moving at high speeds, are increasingly prone to traffic collisions. Vehicle-to-vehicle communications help prevent these collisions from happening. They do so with the help of basic safety messages that are used to exchange information regarding vehicle states and any occurring collisions. They apply digital signature verification to verify the integrity of the BSMs. However, because digital signature verification is a computationally intensive process, there exists a BSM verification bottleneck vulnerability in current V2V systems, which we have analyzed on specific Qualcomm chipsets. Due to this processing limitation, current V2V chipsets can only process a maximum of 250 BSMs per interval, after which they enter a message gridlock state, as you can see in this figure. In this state, receiving vehicles may then discard a random subset of received BSMs. Here we consider an example scenario based on high traffic conditions on the Interstate 490 just outside Rochester, New York. Assume a collision takes place and a critical BSM with information on that collision is sent. Because the receiving vehicle is in a gridlock state, it may discard this critical BSM, leading to another collision. In the presence of an attacker, this gridlock state might occur sooner, as an attacker can send a burst of BSMs in an interval, making the receiver discard more BSMs. To mitigate this, we argue that some BSMs are irrelevant, example those coming from vehicles on the opposite side. We can discard these BSMs to ease the bottleneck, as we will see in this presentation. In our work, we make the following contributions. We analyze the BSM bottleneck vulnerability with the help of traffic simulation software and show that on dense roads, more than 10% BSMs get discarded. We develop different BSM gridlock attacks to exploit the vulnerability. And finally, we develop a filter to discard irrelevant BSMs at the physical layer itself, so that it does not perform digital signature verification and take up significant processing load. First, let's look at our threat model. We consider the direct short-range communications protocol of V2V on a rectangular stretch of road. We assume the attacker is situated off the road, as its main goal is to disrupt the natural flow of traffic. We develop two types of attacks. First is a simple attack in which an attacker is simply sending a burst of BSMs in a single interval to overwhelm the victim vehicle. But this simple attack can be easily mitigated with the basic filter. Hence, we develop a stronger attack that can circumvent a basic filter by applying an artificial carrier frequency offset on the transmitted BSM signal. To analyze the bottleneck vulnerability, we perform simulations on a commercial traffic simulation software where we track the number of BSMs generated per interval. This quantity depends upon the vehicle density, which involves average speed of the vehicles and the spacing between the vehicles. It also depends upon the communication range of the receiving vehicles and characteristics of the roads, such as the number of lanes on the road and whether it is a one-way or two-way road. We simulated different scenarios pertaining to different types of critical BSMs. First, we analyzed the forward collision warning BSM, which is used to prevent rear-end collisions. Our simulations show that vehicles may discard BSMs with more than 12% probability. This can increase by 40% in the presence of an attacker. If a collision takes place and an FCW carrying information on this collision is sent out, but it gets discarded, more collisions may take place as well, resulting in a pileup. We also considered the lane change warning BSM used to prevent side swipe collisions when vehicles are changing lanes. Here the same probability is more than 34%, which increases by 18% in the presence of an attacker. Once again, if this BSM gets discarded, a side swipe collision might occur. We have seen that this processing bottleneck vulnerability can lead to severely unsafe outcomes with a significantly high probability. To help mitigate this problem, we propose a BSM filtering technique that can identify BSMs coming from irrelevant vehicles, such as vehicles on the opposite side of the road, or malicious BSMs that may be sent by an attacker. Our filter subsequently discards these irrelevant BSMs at the physical layer itself, allowing the receiving vehicle to handle significantly more BSMs that are relevant to it. To perform this filtering process at the physical layer, we first developed a naive version of this filter, which utilizes carrier frequency offset estimation. We know that vehicles have relative velocity between them, which creates Doppler shift that causes a frequency offset on the signal used to send these BSMs. The estimated CFO accounts for both the Doppler shift and the frequency offset due to hardware imperfections. Using existing techniques, we can separate the Doppler shift from the CFO and finally derive the relative velocity of the transmitting vehicle. Based on the relative velocity, we can discard irrelevant BSMs. Example, relative velocity of vehicles on the opposite side is much larger than those on the same side. Discarding at the physical layer means the BSM won't undergo the computationally intensive digital signature verification process that happens at the upper layers of the protocol stack. Existing techniques rely on this verification to validate the velocity of vehicles. But in contrast, our technique takes significantly less processing load, involving only a few addition and multiplication operations. As seen in this graph, this basic filter performs well with benign vehicles and even in the presence of a simple attack. However, it can be easily circumvented by a smart attack which reduces its filtering accuracy to almost 50%, rendering it completely ineffective. This is because an attacker can apply an artificial CFO to its transmitted BSM signal and emulate a vehicle moving on the same side of the road. To help identify smart attacks, we developed an improved filter that leverages rate of change of relative velocity of transmitting vehicles. We know that for benign vehicles moving in the same traffic column, the rate of change of relative velocity is small, as we can see in this animation. This is because vehicles moving in the same traffic column tend to maintain the flow of traffic. But this is not true for the attacker that is situated outside the road, who would have larger rate of change of relative velocity. To effectively counter this improved filter, an attacker will need to track changes in the relative velocity and adjust its artificial CFO accordingly, which it cannot do in the same interval the BSM needs to be sent. Hence, we can use rate of change of relative velocity to separate benign and malicious BSMs in a smart attack. We see our improved filter performs with more than 80% accuracy at SNR greater than 6 dB. Note, we are not just leveraging Doppler shift to estimate relative velocity, but also applying additional analysis on the relative velocity to identify malicious BSMs which is novel to our work. Before we conclude, here is a short video of our experimental setup. We implemented a physical layer filter on LabVIEW and used two USRP N210s, one receiver emulating a victim vehicle and one transmitter sending both benign and malicious BSM packets. In conclusion, we have analyzed the BSM bottleneck vulnerability in current V2V systems. We have developed a simple and smart BSM gridlock attack to exploit this vulnerability. And finally, we have developed a physical layer filter that can discard irrelevant BSMs with and without the presence of attackers with 80% accuracy at SNR greater than 6 dB. Thank you for attending our presentation.
Okay, thank you. So this brings us to the Q&A session, and we'll go in the same order as the presentations we have seen. So we start with the first one. And I see that there are on Slack already 2 questions that have already been answered by Domine, but Domine, by the way, can you come online? Here you are.
Yes, hello.
Hello. You already answered them, but maybe for the people who don't have access to Slack, we can still go to them. You can briefly mention what you have said there. So the first question, it was in fact one I also want to ask you yourself. Did you find any relationship between the economic state with some type of metric of a region and then the adopted Wi-Fi security practices?
So it's difficult to define these metrics, but if we look at a few distinctive neighborhoods in the city of Boston that we surveyed, we find that in the neighborhoods that are more likely to have students living there have better security metrics. And a reasoning for this could be that these students tend to move in and move out a lot more frequently than the more permanent residents in Boston. So they might be more likely to buy new hardware, which then offers the most recent security capabilities, which could then be a reason for why the metrics are a bit different there. But overall, I think that the major takeaway there would still be that it is the impact of the internet service providers, which really creates this difference, since they can enforce their default configurations.
And maybe as a follow-up of that, what maybe makes then the difference between an ISP in Belgium and an ISP in Boston? Why is one deploying faster? Do you have any reason for this or no?
It's we have been asking the ISPs in Belgium for years to remove deprecated protocols, but they don't do this. So it must be their own business decision to see what protocols they support or not.
Thank you. And then we have another question also related to the first task about, so this is about enterprise Wi-Fi alliance applications such as Passpoint. They are becoming quite popular. And do you have any insights in terms of trends and best practices for such networks?
We have not explicitly looked at Wi-Fi Passpoint, but it is a security standard we can measure with the beacon frames and the probe responses that we have. So from the data sets, we can analyze the adoption rates of that. So that's all possible with the data sets that we have now published then online as well.
Okay, so that could be an interesting follow-up. I don't see any other questions about the first task, so let's move to the second task second talk, and that's also your talk. There is a question from Peter. Would it be possible for an adversary to sniff an FTM exchange between 2 devices and determine the position of both if their processing times are guessed? And is there a lot of deviation between the processing times of different devices?
So this would then, of course, be implementation specific. So it depends on the vendor, but by default, this might be likely, yes. And that is why one of the countermeasures we proposed in the paper is to add certain random time delays between the frame exchanges, such that it becomes impossible to predict, or to at least accurately predict, what these processing times are, and therefore you would be unable to measure these distances.
I have also a question myself. So in the countermeasures, you mostly focused on the physical layer countermeasures, but as you have shown, you have also problems in the protocol layer itself, can these be easily fixed or not?
It is a difficult protocol to fix, at least within the current capabilities of the Wi-Fi specification. But on the protocol layer, you could come up with certain cryptographic solutions, but they would then, of course, come with a trade-off on accessibility and the seamlessness of these systems. So say you are trying to position yourself in an indoor shopping center, and you would have to authenticate with each of the access points, then this has some accessibility implications. And since these kind of networks may even use like a pre-shared key network, then an adversary can also retrieve the encryption keys since it's a shared password. So then you still really haven't solved everything. So until we can also secure the physical layer, then there are no full solutions for at least the secure distance measurements using the protocol.
Yeah, I see that Peter also thanks you for answering his question. I don't see any other questions regarding your second talk. So I think that's it. If there are further questions, I guess you can answer them on Slack. So
thank you.
Thank you. So let's move to Siddharth. I hope I still pronounce your name correctly.
You can call me Sid, but thanks.
Let me see. Yeah, okay, there's one question for you already. So first of all, people say that you're nice work, you could talk. Is there any evidence of these attacks being deployed in the wild?
That is a very good question asked by Murtaza. So to perform these attacks in the wild, there needs to be the presence of a tense environment with a large number of V2V enabled vehicles, so that there's a lot of PSMs that are being sent around from between all the vehicles. Although that is not currently the case, trends show that in coming years, there's going to be a lot of semi-automated and automated vehicles on these busy, dense roads, where there's essentially going to be V2V communications being used all the time, especially because BSMs are actually quite valuable in these scenarios, which also not just provides enhanced driving safety, but for automatic vehicles, vehicles driving by themselves, it also provides additional information. In those scenarios, these tense environments will become quite prevalent. And in that case, such BSM bottlenecks will occur quite commonly, and such attacks will definitely be possible. However, currently that is not the case, and we weren't able to perform that simply because of that limitation in the today, basically.
One thing I was wondering myself is about the false negative rate. Is there a probability that your message filtering would filter out legitimate PSMs or relevant PSMs?
That is correct, yes. In our current implementation of our filter, the false positive rate and the false negative rate was present. It was, however, under 10% based on the study, based on the limited testing that we did in our lab environment. This is still an ongoing work. We are still performing more experiments and performing more research on even on other types of BSMs as well. So as we train the filter further, or should I say more concretely, when we develop a more consistent filter and more concrete filter, this would definitely decrease the false negative and positive rates.
One other question I had, I'm still looking that there's no other question from Slack. Can you give some insights in how long the filtering takes? Is it milliseconds, seconds? How long would it take to perform the filtering?
So because it occurs at the physical layer, as soon as a packet is received, it initially obviously performs the first of all estimation of where the frame starts at the physical layer. It first performs where the frame starts using the preamble that is used in these frames, and once that happens, after we are able to estimate the carrier frequency offset, because we are using the preambles in the physical layer frames to estimate carrier frequency offsets. Immediately after that, we can derive the relative velocity of the vehicle that sent that frame. So right there, if that relative velocity based on our filter deems that this vehicle is irrelevant, we can discard that BSM right there. So in terms of how long it takes, it essentially takes as much time as it takes to perform timing estimation and performing carrier frequency offset estimation at the physical layer.
Thank you. Let me check. I don't see. Let me check this one. I don't see any other questions, so I think we probably can conclude the Q&A session here. Thank you again. So this is the end of the technical sessions of today, but it's not completely finished yet. We still have our social event on Kadertown, so I invite you all to go over there. And then for the people going for the technical sessions, then probably we see each other tomorrow. And I think Christina still wants to say something.
Thank you. Thank you, Dave, for handing it over back to me. I wanted to use the opportunity to express big thanks to the three session chairs of today, Gerhard, Hancke, Erik, Tews, and Dave Singeley, for guiding the sessions, and of course to all the authors and presenters for telling us about the work that you have done. We've seen the first three sessions today on IoT security, on Bluetooth and ZigBee security, as well as on Wi-Fi and vehicular network security. I wanted to point out as well that we, like the first three papers of the second session of Bluetooth and ZigBee, are all papers that received the replicability label. This is what we need as a community. We need to have data that is collected and made available afterwards, software that is developed and made available afterwards, and allowing for research results to be checked and verified and built upon further. So I just wanted to express my congrats again to these three papers for assuring these labels. A short heads up for tomorrow. We will start tomorrow morning with a keynote talk by Wenjuan Xu about artificial intelligence and IoT. So we will continue with the topic of IoT again for the first session tomorrow. We will then have technical sessions on mobile phone security, on attestation, as well as on crypto. With that, this concludes our Zoom meeting of the first day, but we are not done yet for today, as Dave just mentioned. Please join us on GatherTown, and the task is to talk to at least two people there, at least one of the persons you have not seen for a while, you have not talked to for a while. Try to find somebody that you know, and also try to have a 3-minute chat with somebody you haven't met yet, as the way how it would happen in a physical conference when you just run into somebody. Try to run into somebody on GatherTown and get a short chat started. The links to the GatherTown instance, as well as the password, is available on the Slack channel under GatherTown. So just go there from Slack and you'll be able to connect and meet us there. So I will move over there now. Mathy is moving over there now, and I hope you will join us. And for the others, see you tomorrow again.